In this video, we're going to have a look at the 2023 Tech Active exam. So we're going to start by going through all of the questions in order from multi-choice all the way down to the last extended response. All of the questions that we go through will be chaptered in the description, so you can click and look at the specific ones that you're struggling with rather than having to watch the entire video. But okay, to start with, we are looking at question 1 here. We want to know the amplitude and the period of our circular function. Now, when it comes to the amplitude, you might be tempted to just grab whatever's out the front here as your amplitude. Not quite right. So the amplitude specifically is defined as the distance between the midpoint and the peak of your circular function. So if I were to draw what that might look like, if we imagine our generic circular function, it would look something like this. The amplitude is this distance here. And because it's this distance here, it must always be positive. Doesn't matter if this was flipped on its head, like that, for example, it would now be this that is considered your amplitude, because it's always a distance between the peak and the mid-level. So for that very reason, instead of saying negative a half, we have to say positive a half for our amplitude, which means we only have the possible answers, D and E. Now, with that in mind, we need to find the period of the circular function. The only thing to watch out for here is that the n term isn't already factorized. So usually we think of circular functions as having something to the effect of, let's say, sine n bracket x take h, right? It would be something like that, where the n term is factorized off of the x, but also off of the horizontal translation term. We don't have to worry too much about that. As long as you know that n is always the coefficient of the x, then that's all that matters. So in this case, the period, capital T, must therefore be 2 pi on 3, since in this case n is 3. And that gives us the only possible answer of E. Next up, we have question 2. So we have a parabola that is generic, and A, B, and C are all real numbers. So they can be basically anything they want. And the equation of the axis of symmetry is what we're trying to find. Now, with that in mind, what is the equation for any axis of symmetry? Well, any axis of symmetry for some quadratic y equals ax squared plus bx plus c is always going to be given by x equals negative b on 2a, right? Where the b comes from the coefficient of the x and the a comes from the coefficient of the x squared. Now, that's slightly different to what we're given here. We're given ax squared plus 2bx plus c. So don't be tricked by the fact that this is 2b, right? It's using the exact same letters as would be used for the quadratic, but the full coefficient, that full 2b, is considered our b term for this. So if we go ahead and plug everything in where we expect it to be, negative b is just the negative of this coefficient. So we're going to have negative 2b on the top. And then 2a, well, a hasn't changed. A is still perfectly fine as the coefficient of that x squared term. From there, the 2's are going to cancel down, and you're left with negative b on a, which is going to give you answer A. On to question 3. So we're having two functions here, p and q, and they are continuous functions. Specifically, they have individual domains -2 to 3 and -1 to 5. And we want to figure out what the domain of the sum of those two things must be. So the key thing to watch out for here is that you can only ever do arithmetic on functions where their domains overlap. So if you find it difficult to see exactly where they overlap just by looking at the numbers, then this is where drawing a number line can be kind of nice to help you out. So if we draw our number line, the smallest number is -2, next smallest would be -1, we got 3, and we got 5. So if you imagine drawing that number line, -2 to 3 would look something like this. -2 to 3, you'd have a dark circle on the -2 and an open circle on the 3 to represent whether it's included or excluded. And then -1 to 5, well, -1 is not included and 5 is included. So when you do the sum of the functions, it has to be the intersection of the domains. So it's going to be from -1 to 3, right? So -1 to 3 would be E in this case. So just as a quick visual as to what that might look like, you might have, okay, so if you imagine these x values are are transposed down, or either using the exact same x values, then one function might look like, say, that. Another function might look like that. And so when you add these functions together, you can only add them in this spot here. Because whenever you add a value to something that is undefined, the net result is undefined. Now for question 4. So we have a system of linear equations, and we want to know for where there are infinite solutions. So very quickly, infinite solutions just means that your graphs completely overlap. So these are linear equations after all, so they're all going to look something like this, right? They're just a straight line, linear. For infinite, it just means that both of those lines overlap each other completely. So what that means is, if you want your equations to be having infinite solutions, it basically means that you want them to be the same equation. Mathematically speaking, we only care about the fact that they have the same gradient and the same y-intercept. So you want the same m value and you want the same c value. So how do we achieve that? Well, one of my recommendations would be kind of like how you handle this normally with your tech-free, which would just be to rearrange to get them into y equals mx plus c form. At least that's the first step I'd recommend. This is tech active, so we can use our CAS to help with that. So we're just going to type out things. K times x plus 5y equals k plus 5, and we're going to rearrange for y. Now, one thing worth mentioning here is when you have two letters that are multiplying by each other, don't just write kx, write k times x. If you just put the letters back to each other, back to back, the CAS will consider kx to be the variable rather than k times x as individual ones. So just make sure you put that multiplication in there. We're going to do the exact same thing for the other function. So we're going to have for x plus bracket k plus 1 times y equals 0, comma y. So we now have two equations that are rearranged in y equals mx plus c form. So if we want the same gradient, then what we would want to do is look at both of these equations and figure out, well, what are the gradient terms? The first one is here, right? -4 over k plus 1. That's our first gradient term. So we'll put that in there, -4 over k plus 1. And we want that to be the same as the gradient from the original, the first equation. So the gradient of that would be -k over 5. Right, it's just everything that impacts on that x variable. That's the only thing we care about. So with that in mind, we're just going to equate that to -k on 5. Solve that for k. That's probably going to give us two solutions. It's going to give us k equals -5 or k equals 4, which is normal. That's what you would normally get when you did it by hand. So what we have to do now is make sure that we choose the only k value that would also make sure that there is no y-intercept. So we can look at the y-intercept portion of our first equation, and we can pretty quickly realize that the y-intercept portion is just this bit here, the -k minus 5 over 5. And pretty quickly you can imagine if you were to sub in the -5 for k, that whole thing would disappear. You can test that if you like. So you can go ahead and say negative bracket, -5, where was it? -5 bracket, minus 5 over, well, 5. And you can very quickly see that goes to 0, right? No y-intercept, no y-intercept. So since those are the same, we choose k equals -5 to be our answer, which would be B, answer B. Moving on to question 5. So, which of the following has a horizontal tangent at 0, 0? Well, the easiest way by far to solve this kind of question would be to not think very hard about it at all, and would just be to say, well, for anything to have a horizontal tangent just means that the line is perfectly horizontal, or at least the gradient is 0 at that spot, right? It's perfectly flat. So if we want to know which one of these has a gradient of 0, well, we can just go through the CAS and see which one has a gradient of 0 at that spot. So you can go through menu 3.1 for your solve, find the derivative of the first function, so that would be x to the power of -1 over 3, and see is there a solution for x where it equals 0? There is not a solution for x where the gradient is 0. Well, okay, can rule that one out then. Next one up, power of positive a third. Let's try that. And we should know from our previous studies that that is a perfectly vertical line at 0 instead of a perfectly horizontal one. But because we're doing the mindless approach, we don't have to really think that hard about it. Moving on, 2/3. No, nothing. How about 4/3? Ah, there we go. So we know that we have a perfectly horizontal gradient at x equals 0. But that's not specifically what was asked. We want to make sure that it's at the origin, 0, 0, not just x equals 0. The y value of this could have been something else. Now, if you're looking at your function, you pretty much already know off the bat that it's not going to have, well, if you were to sub in x equals 0 there, you would get y equals 0. But if you're doing a mindless approach, then all you would want to do is, well, instead of putting x there, you would put 0 there and just verify that it does indeed have a y equals 0 as well. Alrighty, moving on to question 6. So we have a sequence of integrals here, and we have to use the values of those integrals to rewrite the third integral there, so 7/3 of f of x, purely in terms of the previous ones, which were in terms of c and d. So the way this pretty much always works is that you're given one integral that covers what you could think of as the entire interval. So this entire interval is from like 3 to 10, we'll say. So if we imagine drawing that full interval from 3 to 10, might look something like this. And there's some function that's in the way here. Doesn't really matter what that function is. Let's just draw some whatever curve. And we're told the area over that full interval is equal to c. We're also told that from 7 to 10, we have a different value. So let's imagine this is from 7 to 10, and that's that interval or area, d. And this full thing, this full added area, is going to be c. Now, we now need to figure out what the value of 3 to 7 is, or 7 to 3, I should say. It's back to front. Which means we're specifically looking for this section of the interval. So one thing we can pretty quickly say is that this full 10 to 3 or 3 to 10 area is, like, you can consider it the full area. So we can say that that full area, C, so the full area there, is equal to D, which is a portion of it, which was from 7 to 10, but also the addition of 3 to 7, that integral of whatever f of x is. And the reason that's important is because it gets the interval that we're trying to find in an equation with c and d. Now, I haven't written exactly what was in the question. I did 3 to 7 instead of 7 to 3, but we'll fix that later. All we have to do now is get this integral on its own. So we're going to do c minus d is equal to that integral. Now from here, when the terminals are flipped, it's the same thing as if you had replaced what it equals with a negative sign at the front of it. So flipping the terminals will always flip your area from positive to negative. So if we flip these terminals back to 7 to 3, which is what they were, all we have to do is put a negative sign at the front of our c minus d. And then from there, we're just going to distribute that through. We're going to have, now it's going to be d minus c as a final answer, which if we look at what we have, is going to be answer D, d minus c. Okay, on to question 7. So in this case, we want to know the domain of the derivative of a composite function. So that's a little bit different. Usually it's just what's the domain of the composite function. This time we have to care about the derivative of our composite function. So one thing that's worth discussing here is how you even find the derivative, or how you even find the domain of a composite function. So the way any composite function works is something like this. Let's say we're considering f of g of x, right? That's the composite function that we have, f of g of x, or you could say f o g, like we have here, f o g of x. Both of those mean the same thing. So the way this works is that you have an inner function and you have an outer function. So what we can imagine is that we have some x value and it gets fed into the inner function to start with, right? It gets fed into g of x. Then from there, whatever the y value is from g of x then gets fed into the outer function, which in this case is f of x. And then finally, that gives you your final y value. That's how composite functions work. So if you think about each stage of the process here, each of these functions has an individual domain and range, right? Like there's only so many values that can fit into g of x, and there's a different, maybe a different number of values that could fit into f of x. And so if you think about the domain of the entire process as a whole, if it can't fit in here, then it's never going to get through to here. So when you think about the domain of a composite function, it's always going to be bottlenecked by whatever the inner function is. So the domain of any composite function will be the domain of the inner function, where in this case our inner function is g of x, the inner function is g of x equals root 1 minus x. Now from this one, you can either rely on your ability to understand what the graph is, or you could literally just graph it, because this is tech active. So just so you can see a little visual, if you do square root of 1 minus x, you'll quickly see what the domain of that is going to be. And that's going to be all x values that are less than or equal to 1, which that's nice, right? We have our initial domain. Domain is x values less than or equal to 1, but that's not quite what was being asked here. We wanted to know the domain of the derivative of FOG. So this was still important to understand because the domains do pass through, right? Domain of your original function does cascade down to the derivative, but there are some circumstances where it might get a little bit weirder because, you know, sometimes when you have divide by zero errors, it introduces more ways in which the domain of your derivative might be slightly different to where it started. So let's actually find, well, first of all, find our composite function and then find its derivative. So we can just make use of the define function in the CAS to help us out here. So I'm going to call, you know what, let's use the actual wordage. So we have f, where's f? F of x is equal to natural log x. We have g of x, which is equal to, well, I just did that one, root 1 take x. So f of g of x, f of g of x would look like that. All right. So what we want to do is find its derivative. So d dx of f of g of x. And that's going to give us 1 over 2 bracket x take 1. Now, if you're looking at that, one issue that comes up is, as I mentioned before, this fact of a divide by zero error. If x was equal to 1, then you would have a divide by zero error. So we're just going to look at that previous domain that we had. Domain is x less than or equal to 1. And then we're just going to drop that down a little bit. Domain is x less than 1. Which, if we're looking at our possible answers, x less than 1 would be C. Right, we're non-inclusive of that one. Okay, question 8, all about probability. So, in this case, we have a box of n green balls and m red balls. Ball is selected at random, color noted, and replaced in the box. So every time a ball is selected, it gets replaced again. So that keyword there being replaced means that this is very likely to be a Bernoulli sequence. In fact, it is going to be a Bernoulli sequence, right? We have repeated trials that don't change the probability from trial to trial, and so this is why this would be a Bernoulli sequence. There are other criteria, but that's really all you have to care about. We have 8 selections, so 8 total balls were drawn, and we want to figure out the probability that a green ball is selected at least once. Okay, so first step for this sort of thing would be to just write out what is your probability of that thing occurring. So let's say we have probability of, we'll call it G. G is greater than or equal to 1, right? That would be if you have a green ball selected at least once or more. So how much you find this with your Bernoulli sequence? Well, there's a couple of ways you can go about it. If you're looking at all the possible answers in your multi-choice, you realize that they're not like supermassive, right? They're all just 1 minus something, with the exception of A, of course. And that should really clue you into the fact that we don't really want to be adding 8 separate Bernoulli sequences together, because that's how you might do it, right? G greater than or equal to 1, you might do G equals 1, G equals 2, G equals 3, and so on, and add it all together. But the alternative is to use the complement probability, which would be 1 minus the probability of G equals 0, right? It's just 1 minus everything else that could possibly occur. That is a lot easier to find and clearly a lot better for what we're looking for, because all the answers in the multi-choice are 1 minus. So that begs the question then, what does the probability of G equals 0 look like? Well, that is a Bernoulli sequence sort of thing. What is Bernoulli sequence? Well, let's go and have a look. Bernoulli sequence is right here. So you've got your binomial coefficient, the NCR type thing, and you've got your probabilities here. So how does that work? Well, we need to know our n, which is the number of trials, 8 in this case. We need to know our x, the number of balls that we're selecting, which in this case is 0. And we needed to know p, the probability of selecting the ball. For that one, I'll have to have a look. Let's remind ourselves what that was. So we're doing green, so probability of getting green. So we're not actually told that off the bat, but we do know how to find it, because the probability of getting, so PR green at all, the probability of getting green is just going to be based on how many balls there are in the box and how many green balls there are in the box. There are n green balls in the box, and there are n plus m green balls, total balls in the box. So that is going to be our probability for green. All we do from here is do our Bernoulli sequence. So if we know that's our probability, let's just go back so we can have the Bernoulli sequence on the same screen. So there it is, starting with the binomial coefficient. So we're going to have n, which is 8, so it's going to be 8 factorial. We're going to have x, which is 0, 0 factorial. We're going to have, okay, n and 0 again, factorial, and the p values. So I'm just going to use this p so we don't have to rewrite the same thing a lot. X is going to be 0, and n minus x is going to be, so 8. Bracket 1 minus p, and then 8 is going to go there. That's just 1. This will also just be 1, because 0 factorial is 1, and 8 minus 0 is 8. So you're going to have a factorial and a factorial. Anything divided by itself is 1. So all of that's going to disappear, and you're just going to be left with the probability, so 1 minus p, the power of 8, where p is this thing here. We take a quick glance at our multi-choice possibilities. I suspect we'll see it. Is that one it? Part C. So 1 minus m, nah, not quite. So it must be B then. 1 minus n over n plus m to the power of 8. Yes, that's the one. So that's how you do that one. Okay, question 9. So the value of a for which f is continuous and smooth at x equals 2 pi. So at that crossover between the two composite, well, between the, not a composite function, it's a piecewise function. So how do we get continuous and smooth at that spot? Well, you could do a lot of effort into actually calculating what that would be, right? So for continuous, you want to make sure that the values are the same at 2 pi. So if I sub in x equals 2 pi into the first function, I should get the same y value as x equals 2 pi in the second function. And then the smooth aspect there is that the derivative must also be the same at that spot. So the derivative of the first function at 2 pi must be equal to the derivative of sine of the derivative of that second function at that spot. That would take a fair bit of work. Alternatively, you could just plot this on a CAS and then just sub in each of the possible answers and then just see which is continuous and smooth at the same time. That's what I think I'll do. So with that in mind, let's get to sketching. So we can do our piecewise. We're just going to click this button here. Let's get rid of the shadow. There we go. And it's this bit that I've highlighted here. That'll allow you to put a piecewise in there. We specifically want to have not 4, but 2 different pieces for the piecewise. And we're going to just plug those in. So we have tan of x over 2. And we're doing that from 4 less than or equal to x less than 2 pi. And we have sine ax. So we have sine bracket a, remember, times x. Well, we didn't have to do an extra set of brackets, but the only thing we had to really care about there was putting a multiplication sign between the a and the x. Otherwise, the CAS will complain. And that is from 2 pi less than equal to x less than equal to 8. Cool. I'm going to hit enter. It's going to say, hey, I want to have a slider for this because I don't know what a is. That's fair enough. We can have that. And if you just sub in, well, currently it defaults to a equals 1, you see that that's what the piecewise is going to look like from our given domain, from 4 to 2 pi, or 4 to 8, I guess we should say. So let's just set our window settings so we can actually see what that's like. 4 to 8, and we can a bit nicer see what's going on. Now a equals 1 isn't one of our possible solutions, so we can ignore that, whatever's here. I'm just making the window a little bit bigger so we can see either side of it. Okay, let's see if we can make that a bit, yeah, that's clearer. Cool. So you can see it's got a little bit of bump there already. It's probably not going to be what we're looking for. So let's go down the list. So let's try a equals 2, because that's the, well, I guess negative 2 is the first one. Does a equal negative 2 work? No, that is very much a sharp transition. If I move this out of the way a little bit, you can move these things by just long pressing on it and then drag and drop. Click again. So that is definitely not smooth at that spot. The next easiest to try would be, well, it's a bit, I don't know if you can put pi in this. Let's find out. Can we put negative pi? Yeah, we can. Nice. Negative pi on 2. Nah, that's not even continuous. Yeah, it's got that little dip, or the break. We don't want that. So I'm just going to jump in there once again, and negative a half this time. So negative 0.5. Is that going to do it? Oh, we might have a winner there. So we should really zoom in on that 2 pi spot. So if I do -41 to get our window settings, I'll do 2 pi minus a small amount. Let's say 2 pi minus 0.1 and 2 pi plus 0.1. And we can really see if that's going to be smooth or not. And that looks pretty damn smooth to me. So I would go off and say negative a half would be a solution to that. You can also go ahead and test the remaining possibilities just to make sure that those are not also looking like they're smooth. Like for example, if I do regular 0.5, zoom out a little bit so we can see it again. Where is it? It was 3 to 9 if you wanted to see the full thing. You can see if you zoom out there, it's quite clearly not smooth there. And the last one would be 2. Let's double check. So if you check 2, you get another sharp transition. So the only one that looked smooth would be C, and therefore I would choose C. Alrighty, next up, question 10. So the value of k for which the probability that x is less than k is equal to 0.35. So whenever you have probabilities that are piecewise functions, you know you've got a continuous probability on your hands, which means if you're trying to find probabilities with that, you need to work with integrals. So just strictly speaking, the probability of x less than k would be something like this. If you imagine that you have some curve, now it's not going to be a bell curve, but we don't really care. If you imagine some k value, then x less than k would just be all of this area here, everything less than k. And we want to make sure that everything from here to here is a probability of 0.35. Now, this is obviously not to scale. If it were to scale, k would be somewhere over here instead, right? It's a much smaller area than the area that's depicted there. Point being, you want to make sure that everything left of k is equal to 0.35, and you want to figure out what k must be for that to be true. Well, the problem with the piecewises is that the area of your integral, when you try to do your integral, you have to figure out, is the area 0.35 going to belong to the first section or a combination of the first section and the second section? So to figure that out, the first thing I would be doing is testing that first area. How big is it? So if we go through and test that, so find the integral from 1 to 6, I just want to know how big is that first section. X take 1 on 20 dx, how big is it? It's 5 out of 8, which is 0.625, which is well and truly bigger than 0.35, so we know for a certainty that the area 0.35 is only going to belong to this first section. Now that we know what function we are trying to integrate, now we actually try to solve the question. So k is an upper bound in this case. It's everything less than k. If you look at the little picture again, it's everything less. So it could be from here to here to here. It doesn't really matter what the function looks like. K is always the upper bound in this situation. So when we go ahead and do our solve, because it's always a solve, we're going to set, whoops, that's the wrong one, not derivative, but integral. We're going to set k as our upper bound, right? Because we don't know what it is, but we do know that it's called k. From there, the lower bound has to be 1, right? It can't go any lower than 1. And we also know the function. We know that we have x take 1 over 20. That's always a given. Now, the interesting thing here is that we know what this equals. We know that it equals 0.35, right? We're told the probability is equal to 0.35 over that interval. So all we have to do is tell the CAS to solve that for k, hit enter, and you're going to see the proper solution, right? It's going to be plus minus the square root of 14 and the plus 1. Now, are both of those valid? Well, if you control enter here, you've got k equals negative and k equals a positive. If you're looking at how that would work, k could not be a negative and still be an upper bound at the same time, right? If 1 is the lower bound, then k has to be at least greater than 1 for our solution to make sense. So we can ignore that first square root term and just look at the second one there, which is square root of 14 plus 1, which is answer B. This one here, question 11, was actually kind of cool when I saw it the first time. It's a very, very interesting use of the product rule. It might not immediately look like the product rule, but when you really dig into what it's actually asking, it's saying, what is the gradient of a product of functions at some point? That's really all it says, right? And that's what the product rule is. So what it means is we need to know, well, first of all, we have to know what the formula of the product rule is. So let's go ahead and achieve that. So whenever you have two functions that are multiplied together, if you want to find its derivative, then you need to make sure that you know, so f dash x equals u v dash plus v u dash, where v and u are the individual functions. In this case, we have f and g, so what I'm going to call it is I'm going to say, I don't know, let's just call this a dash of x, just some random function. It's going to be f g dash plus, that's supposed to be a dash, f g dash and plus, so that would be g f dash. Right, those are the things that we need to know. Now, if you then want to know what is the gradient at a specific point, x equals negative 2, well, it just means that you sub in x equals negative 2 into all of these spots. These should technically have x's in them. So a dash of negative 2 is the thing that we want. So it means we need to know f of negative 2, g dash of negative 2. And we need to add that to g of negative 2 and multiply that by f dash of negative 2, which all of these we do know. We see f and g of negative 2, and we see f dash and g dash of negative 2. So that's what we're going to do. Just going to go through and smash that through on the CAS. So what we're going to do here, let's make sure that it's actually visible. That'll do. Okay. So we need to do f of negative 2 and g dash of negative 2. So f of negative 2 is negative 7, g dash of negative 2 is 2. Going to add that to g of negative 2 is 8, and multiply that by f dash of negative 2, which is 3. That's going to give us an answer of 10, which is answer E. Okay, question 12. Now we're dealing with the probability tables. Maximum possible value of the mean of x. So, what's that all about? Well, if we ignore the maximum part of that question, the first thing that matters there is the mean of x. What is that? Well, for discrete probability, the way that works is that you just go through each individual x value and multiply it by its corresponding probability. Then you add that to the next x value in probability, next x value probability, and so on and so forth. So the first thing we can do is figure out, well, what is the mean of this situation? You can't find the maximum of something if you don't know what that something even is. So we've got to get our equation. So we're going to use our CAS to help us out with that. -1 times k squared is that first bit. Adding that to 0 times 3k, which of course is just 0. Adding that to 1 times k, so, just k. And then adding that to 2 times a full quadratic, because of course, minus k squared minus 4k and plus 1. Cool. That's going to give us a full quadratic there for our mean. We want to know the maximum possible value of this mean. Okay, fair enough. Well, if that's the mean, and the mean is a quadratic, then to find the maximum of a quadratic, typically, we just have to find a turning point. And that is definitely the case here. We have a negative quadratic, which means it's a frowny face quadratic. So if I go ahead and just define this as a function, doesn't matter what it is, what I'm going to do is replace all those k values with x values, so it can actually be plotted. We're just going to plot that on our CAS, and then have a look and see what we have. So go ahead and plot h of x. We're going to have our frowny face parabola, and we're running into an issue here. So the issue is that we can't have negative x values, right? Probabilities can never be negative. So we want to make sure that at a bare minimum, remember, because k is going to be on our x-axis in this case, all of this on this side here, we can't use. So even though our turning point is there, we can't really make use of it. So one thing we'll quickly do is just make sure at the very least that x is greater than 0. Or at least greater than or equal to 0. But it's not so much of an issue when you're just plotting it. We should also pretty much be confident that k has to be between 0 and 1. So we're going to make sure that's the case. And the last thing we need to worry about is that each individual probability has to add up to 1. So one thing I would do from here, I wouldn't worry about that too much right now. Like what I'm saying is, sure, we know from this third entry that k has to be between 0 and 1 because probabilities have to be between 0 and 1. But there is the possibility that you have 3k here, for example. That means that we're actually capped at a third, right? Because if you had k equals 1, that'd be fine for this, but this would be 3 now. That's bad. So that is another thing worth considering. That is a lot more complicated to think about, so I would only look at that if was absolutely necessary. And in this case, it doesn't look like that's going to be the case. For example, if I jump back a slight amount, we see that the maximum with that restriction on the domain is going to occur out here anyway. So I don't have to really think about how far right can it go. I'm already only looking at this left-hand side. I don't actually care how far right it can go. As long as k equals 0 is valid for this probability table, then I'd be fine. So I know this occurs, I know the maximum occurs at k equals 0. So let's try that. What is the value at 0? 2, right? That's way too big. Wait, no, it's a mean. Mean is allowed to do that. That is fine. So we just need to make sure that k equals 0 does make sure that the probability all adds up together. So if you imagine something in k equals 0 at all of these spots, all those probabilities would go to 0, which means that if I were to sub-0 into this, I should get 1, and sure enough, I do. You can see if that goes to 0, that goes to 0, that equals 1. 0, 0, 0 plus 1 equals 1. So not only do we have our mean value of 2, which is correct, we've also made sure that the table adds up as well. All of these things have to be true at the same time. That makes us confident to say that E equals 2 is a valid solution to this. Alrighty, question 13. We're starting to look at pseudocode now. So the good news here about pseudocode is that a lot of the time, you don't even really have to read too hard into the pseudocode thing. Like for example, if you just read the define statement here, it says Newton. So as long as you know what Newton's method is, you already know kind of what that algorithm does, right? You don't have to think too hard at all about that. The only thing you might want to look at here is this for loop here. For loop from 1 to 3. That means that this code is going to iterate 3 times before it exits. So fundamentally, all this is saying here is that we're going to do our Newton's method 3 times over with some initial x value, and then whatever the answer is going to be returned, right? The x naught. We want to know what is the return value for this function under these particular parameters. So how's that going to work? Well, first things first, let's actually get Newton's method into our CAS. How does that work? Well, my recommendation is to define Newton's method in 3 parts. So the first part is going to be whatever the function is that you're trying to do Newton's method on. So I'm just going to call that a of x. So in this case, if we look at our input list, we're told what the order of the inputs are. So the first thing in brackets is going to be f, the second thing is the derivative of f, and the last thing is going to be the x value that we have. So when you look at how the function is declared, this first thing here before the comma is our function that we're trying to do Newton's method on. So we can do a of x is equal to x cubed plus 3x minus 3. Cool. Next thing up, we want to know the derivative of a of x. So let's do that. Don't even need to look too hard. All right, just going to define it purely with respect to a of x. And then lastly is the actual Newton's method equation itself. So that's going to be c of x. Just so you have something to reference, let's go and see what that actually looks like in the formula sheet. So in the formula sheet, we have Newton's method here, which says that our function, xn plus 1, that's whatever the function is called, I've called it c of x, is equal to the previous guess, xn, so we're just going to put x in here, minus f of x, so our f of x was a, divided by the derivative of f of x, that was b. And just like that, we have Newton's method. Now, the good thing about defining it this way is that you can do that before your exam, and then all you ever have to do in the actual exam is replace a of x, and everything else will change, because all these definitions are purely based on a of x. For example, if I hit enter on c of x, then it's going to print out something. If I redefine a of x to be equal to something new, let's say x, then when I reprint c of x, it's going to update. Now, it's going to break because I just put a nonsense whatever in there, but it will fix itself up for when you actually use a proper function. So redefine a of x, and we get back the c of x that we wanted. Okay, so how does this work? Well, if you want to loop it 3 times, then here's the funny thing you can do. You can just do c of whatever the function value starting point is. So we see that the next thing there is x equals 1, so we're going to put c of 1 in there. That's going to give an answer. That's our first iteration. What we're going to do is take that back, plug it in again. That's our second loop. And then finally, our third loop, we put it back in, hit Control Enter, 0.817, 0.81773, which is going to be answer C. So that's the easiest way to do Newton's method. As far as the pseudocode, how do we handle that? Well, we had to start by looking at what was the function called. It was called Newton's method, so we already know roughly what's going on here. We had to look at the for loop to figure out how many times to do it. We had to look at the inputs to figure out what the order of these were. So we know what f is, we know what the derivative is, and we know what our initial guess is. And from there, you should just have Newton's method already defined in your CAS. If you're looking at my lectures beforehand, you would already have that. If not, make sure you have at least 3 you have those 3 variables signed up for your Newton's method. Just put them as whatever things you don't usually use. That way you can have the rest of the keyboard. You've got 26 letters in there. I'm sure 3 of them can go to Newton's method. Okay, question 14. Polynomial and tangents passing through the positive x-intercept. So this is a kind of example where you can pretty much just graph this, and you can almost just flat out observe everything that could come from that. So let's start by graphing it. X times bracket 3x, take 1, times bracket x plus 3 times bracket x plus 1. That's what we got there. So we got some polynomial, I think it's about a quartic, cubic, no, quartic, yeah. Anyway, we want to know how many tangents could pass through the positive x-intercept. So what does that mean? Well, positive x-intercept must just be that. Right, it's the only x-intercept that's on the positive side of things. So we can fix our window size a little bit to see things just a bit clearer. Let's go 5 to 5, and then let's shrink that down ever so slightly more. 5 to 2. Yeah, now we can see things much clearer. So, how's this going to work? Well, first things first, how do we get a tangent to go through here? Literally just lie your pencil across things and see, if you were to imagine taking a tangent line across this graph at any point, where would you get a tangent that passes through that spot? The first natural spot would be literally on the intercept, right? If you were to take the tangent exactly on the intercept, it would go through the intercept. It has to, by definition. So that's one possible spot. The next spot that was possible would be somewhere around here, right? As this gets taller and taller, eventually it'll crest over and hit through that intercept. So that's two possible intercepts. From there, we would have to zoom out a little bit to confirm, but because there's going to be a turning point down there, we can be pretty sure that there's going to be a possibility of a tangent going through there. Let's make it ever so slightly smaller, -20. Yeah, there we go. So you can imagine at that turning point, because it starts turning around, eventually it'll have an angle that will hit there. So we've done 1 from here, we've done 2, we've done 3. Now, if you imagine this entire left-hand side, it's not turning back on itself, right? Doesn't matter where you draw that tangent, the further left you go, the further it's going to go straight up and never reach this spot. So you've got 1, 2, and 3 possible tangents. So the answer is going to be D. Alrighty, question 15. So now we are entertaining the idea of normally distributed random variables. So what's going on here? Well, we have two normally distributed random variables that are plot against each other. One has a different mean and standard deviation to the other. So x has a mean of 100 and standard deviation 20. Y has a mean of 80 and a standard deviation of 10. So you need to know what the mean and standard deviation do to the graph of a normal distribution. First thing to watch out for is that the mean will tell you the x value of the center point of your normal distribution. So if you have, whoops, let's not hit the camera that hard again. So we zoom out just a little bit there. If you imagine drawing random normal distribution, this center point here is the mean, mu, whatever that value is. So if you have a higher value, it's going to shift. If your center point is now at 200 and this was 100, then your new distribution would look like that. So which of the two have a larger mean? Well, x has a mean of 100, y has a mean of 80, x should be to the right of y. So if x is the dotted line and y is the solid line, then A, C, and D are all what we're looking for. But the next thing to consider is, well, the standard deviation. What does that do? Well, standard deviation is a measure of spread. The larger your standard deviation is, the more spread out it's going to be. So this is what a large standard deviation would look like. This is what a small standard deviation would look like. Right? Smaller standard deviation, the more concentrated the probability, the taller the curve. So if x has a standard deviation of 20 and y has a standard deviation of 10, then we expect x to be flatter and smaller than y. So once again, if x is a dotted line, then we expect the dotted line to be flatter and smaller than the solid line. The only one that matches that is A. If you compare to C, the dotted line is bigger. If you compare to D, they are the same size. The only one that's going to be possible for this solution is going to be A. Alright, question 16 looks like it could be quite complicated, but it doesn't actually end up turning out to be all that bad. So we're told what f is equal to, and we're told what the product of f and g is equal to. And we have to figure out what is g. Well, realistically, we just treat this like algebra. right? If you want to find what g is, you get g on its own. So if you have product of f and g is equal to e to the x take 1 all squared, then when you get g on its own, we're just dividing that right-hand side by f. So we have e to the x take 1 all squared, and we're dividing by f, which we know from the top of the question is e to the x take 1. Now, we could go through the math of simplifying that down. I'm not going to do that. We have a cas. Why would we bother? So, g of x is just going to be whatever this simplifies down to. So we're going to have e to the bracket x take 1 all squared and e to the x take 1. E to the x take 1. And if you look at what that actually ends up equaling, we have a quadratic in our product. Sorry, not our product, our exponent. Now, if we're looking at all our answers, they are all factorized. So what we're going to do here is just take a copy of that and factorize it. So many32 for factor. Just hop up the top here, grab a copy of what was convenient, highlighted the whole thing for us. Factorize. I see why I did that. We copied it poorly. That's fine. Just go ahead and copy it properly this time, or just, type it out. You don't have to be lazy like me. Comma x, just so it knows what it's factorizing. Shouldn't really matter if it's only one variable. Which means our new exponent is going to be x take 2 and x take 1. So where do we have that? Well, that's answer B. E to the x take 2, x take 1. All right. This one's a little bit rarer, question 17. Usually we have like boxes to worry about, but this time we have a cylinder. So we have a cylinder of height h, radius r, formed from a thin sheet of metal. We have these initial dimensions x and y, and we have to figure out what the new volume, what the volume of the cylinder would be in terms of x and y. So how do we do that? Well, first things first, what is the volume of a cylinder? Volume of any cylinder is pi r squared h. So let's have that written down. Volume is going to be pi r squared h, where r is the radius of your cylinder and h is the height of the cylinder. So if we're looking at what we have, that's actually already depicted for us, right? We have r as the radiuses of the circles, and we have h as the portion of the cylinder that is cut out from x. Cool. So the challenge here becomes, how do we get rid of these h and r's and get them purely in terms of x and y's? Well, the first thing that's coming to attention is the fact that h is just a cutout of x, and r is just a cutout of y. If you look at how that would end up being. Technically, you could also say that r is a cutout of x. That might be important for the solution. I guess we'll find out. So if we're looking at just the full width of x, I guess you can call that a length. It looks like a length. It's made up of h, so you can say x is equal to h, but it's also equal to the addition of these two circle bits here. So the diameters of those circles, which means 2 radiuses from the first circle and 2 radiuses from the second circle. So we can say that x is equal to h plus 4r in total. Right, so now we have a way to get x into this equation. The next thing we need to consider is the y. How do we get to the y? The y bit is all contained, right? This entire that entire width of that rectangle is wrapped around to make the cylinder. So this y value is the circumference of this circle, right? You can imagine this whole straight bit being wrapped around the circle to create the height of your cylinder. So y is directly equal to the circumference of the circle. What's the circumference of a circle? Well, circumference of any circle is 2 pi r. So y is equal to 2 pi r. So right now we have a way to get y in terms of r. So let's do that. R equals 2 pi, r is equal to y on 2 pi. So every instance of r we can now replace with y on 2 pi. So let's do that. Right now we have v equals pi. Instead of r squared, we have y on 2 pi squared. And then h. And instead of the x here, so we would now have x equals h is what it is, and then 4 times r, well, that's just 4 times y on 2 pi. Yeah, h plus that. So instead of putting a h here, we can now rewrite the x in terms of, well, h in terms of x, so we can get x and y on its own. So if we get the h over, well, that's just subtracting h and subtracting x. So subtract h minus x plus y, 4y over 2 pi. Multiply everything by -1 again. H equal x minus 4y on 2 pi. And that's going to go here. Now that's a lot to try and do by hand. We do have a cas, so let's use that to our advantage. We'll zoom out just so you can see what's going on there. Volume is equal to pi times y on 2 pi squared. Y times, why is it doing that? Pi times bracket y on 2 pi all squared. Should probably do that starting here, and then multiplying by the h that we now have, which was x take 4y, so x take 4y all on 2 pi. Now, I should have put brackets there earlier. That's fine, we'll do it now. And let's compare. So it's done a bit of factorizing there. So you could imagine, yeah, let's put that through and expand. Only 3 to expand. Well, okay, it's done a little bit more than just expand, but sure. Let's see if we can compare that. So basically we're looking for pi x y squared and -2y cubed. -2y cubed, pi x y squared, that's part B, and 4 pi squared. Yeah, so this expansion has gone a little bit too much. It split denominators as well. We kind of just wanted to expand that numerator so it made a match, which is what we have. I'll zoom in a little bit closer so you can see in higher detail what I'm talking about there. If you expand this numerator out, you're going to get answer B. Alright, question 18. We now have to deal with a circular function that has an unknown a in it, and that a is also controlling the width of the domain. So we have from -a pi to a pi, and we have sine a of x. Specifically, we're trying to figure out the number of local minima that will be in the graph over that given domain. So just quickly, if we have a look at how many minima there should be in any given period, we're going to notice very quickly there's only ever going to be one possible minima. So if you think about some generic sine wave, it would look like this. There's your period, and the only minima on that graph is right there, right? You've only got one minima in the given period. Well, the next natural question would be, what's the period of our circular function? Period of sine and cos is always going to be 2 pi on n, where in this case n is equal to a. Cool. The next question would be, well, how many periods fit within our given domain? Because if the number of periods is equal to the number of minimas, then we just need to figure out how many periods fit into the domain. So if you think about what our domain is, we've got -a pi to a pi, and it's going to be like 0 here. That full stretch of length is going to be 2a pi. Right, we've got an a pi here, we've got an a pi here. That's that full distance. So we're just going to figure out how many times does 2 pi over a fit into 2a pi. Or in other words, you're just going to do a division of 2 pi on a. Which means, because it's division, you're going to flip it. So 2a pi multiplied by a on 2 pi. The 2 pi's cancel out, and you're left with a squared. A squared, of course, being answer E. Righty, we're getting to a bit more difficult questions here. Question 19. Find all the values of k such that some quadratic here has two real solutions, one being positive and the other being negative. Well, how do we handle that? As I mentioned already, this is a quadratic, right? You have an x squared, you have an x, and you have a constant. Even though there's k squareds and k's in there, this is a quadratic of x, right? We're finding k. We're K is not the actual thing we're trying to find solutions of. We're trying to find solutions of x. You can see that there, 2 real solutions for x. So how do we figure out the number of solutions? Well, how do you figure out the solutions to this quadratic? Well, step 1 will just be look at the CAS. The CAS should have some answers for us. So all we're going to do is type in exactly what we have there and solve it for x. So let's go for it. 93(1). And got x squared plus bracket 4k plus 3, 4k plus 3 times x. And we have plus 4k squared minus 9 on 4 equals 0. And we're solving that for x. Cool, so that's going to give us 2 possible solutions. One is going to be the positive square root and the other is going to be the negative square root. Okay, you can see both of those there. Now, we need to make sure that one of these is positive and the other is negative. So naturally, you would imagine that the negative root would have to be the negative solution and the positive root would have to be the positive solution. All right, that's typically the best you can really do here. So that's how you could get positive and negative solutions there. So what you want to do is say, well, okay, for what values of k is this greater than 0? Let's give that a shot. So we're just going to copy a specific bit that we want. For what values of k, Control C, Control V, is this, whoops, greater than 0, comma x, no, comma k actually instead. And we can see that will be between negative 3/4 and positive 3/4. We can do a very similar thing for the second section, right? We're going to make this negative. I'm just going to grab the second bit over here and say, well, okay, what would it take to make this one less than 0? So Control V, comma k, don't forget to say less than 0. And in this case, we know that we're good as long as k is greater than negative 3 on 4. So let's have a look at what those inequalities would look like on a number line. That way we can more easily simplify them down. So the numbers that we care about are negative 3 on 4 and positive 3 on 4. And okay, so between negative 3 on 4 and 3 on 4 would just look like this, open circles technically. And then greater than negative 3 on 4 would look like that. So that's both of those there. So the intersection of those two things would just be from negative 3/4 to 3/4. Now, is that our final answer? Well, we also have to make sure that we definitely do have 2 solutions. And the only way that we have 2 solutions is that we have to make sure that the square root term is not equal to 0. Because if the square root is equal to 0, then there will not be 2 solutions, right? You're not going to have a positive and a negative in there. So we're just going to make sure that that doesn't play a role in our solution here. So we're just going to make sure, again, grab a copy of the inside of the square root and say, for what values of k will it equal 0? And we're just going to make sure that we don't include those. Equal 0, comma k. That's going to be at k is equal to negative 3 on 4, which is fine. We were already not including it. So with that in mind, the only possible answer here is going to be D. Alrighty, finally we have question 20, end of the multi-choices. So we have 2 functions, f and g, and we want to figure out where f of g of x and g of f of x both exist. Right, we want to figure out where do both of those composite functions exist. So the natural question there is, what's it going to take for any composite function to exist? I've done this before. So the sequence of how composite functions work is that, let's imagine we're doing f of g of x. Well, it just means that you have some x value that gets fed into the inner function, and then that gets fed into the outer function, and that becomes your final y value. That's how this works. So for a composite function to exist, we need to focus on this transition here, right? Going from g to f. we want to make sure that all of the y values that come out of g can fit inside the domain of f. Because if you imagine this as your y values of g, then if you were to try and shove those into f's a little bit too small to grab all of those, right? The domain of f can't fit the full range of g. Under these circumstances, we say that the composite function does not exist. So we need to make sure that the range of g fits inside domain of f, at least in terms of f of g of x. If you have g of f of x, then you have a slightly different look. You now have f here. Then that gets fed into g, and then that becomes your y. So under these circumstances, you want the range of f to fit inside the domain of g. So we need both of those things to simultaneously be true. So let's write that out. So we want to make sure that range of g fits inside domain of f, and you want to make sure that range of f fits inside domain of g. Well, how are we going to do that? Well, a good starting point would be to figure out what do we have currently. So if we think about what we have already, looking at, let's say g, right? G is pretty quick. G is just sine x. So if g of x is sine x, then we know that the domain of g is actually already told to us. So domain g is equal to negative infinity to 5. Negative infinity to 5, both non-inclusive. And the range of g is just going to be from negative 1 to 1. Right, it's a circular function, it has an amplitude of 1, and so the range of g is going to be from negative 1 to 1. Cool. So on to f of x. Now, f of x is just a logarithm that's been shifted left by 1 on root 2, which means, yeah, let's put it here so we can compare them directly. F of x equals natural log x plus 1 on root 2. So for domain and range of that, we can say domain of f, since it's been shifted left by 1 on root 2, we have negative 1 on root 2 all the way to infinity. And then the range of f, well, that's just going to be all real. There's no cap on that. It shoots all the way down and all the way up. And you can sketch these if you like. So we just want to make sure that both of these are true. So what's it going to take to get the range of g to fit inside the domain of f? Well, range of g is this, domain of f is that. Well, negative 1 is bigger than negative 1 on root 2 already, so we need to cap this section off to negative 1 on root 2. And 1 is smaller than infinity. So for this to be true, we need to make sure that the range of g is the new range, so we can say range star of g must be at maximum negative 1 on root 2 to 1. Right, that's the new maximum for that. Similarly, we can do range of f to domain of g. So range of f is all real, domain of g is negative infinity to 5, hence the new range of f, range star of f, must therefore be equal to the domain of g. So negative infinity to 5. That's as big as it could possibly be. Those are our targets. We need both of those things to be true. How do we do that? Well, the only way you can ever change the range of a function is to change its domain. So we're just going to go back and figure out, well, what would it take to make this happen? What's the largest possible x values? So all we're going to do is plot those. So when you plot them, it'll allow you to figure out pretty quickly what it's going to take to achieve that. So I'm going to open up our graph. First things first, nice and easy would be to just work with sine x. That one might be the easiest to start with. And the domain of sine x is currently from negative infinity to 5, so we can even put that in there if you like, although yeah, that would just be x less than 5. Nothing too special there. X less than 5. Now, if you want to cap this out at negative 1 on root 2, then what we could do is just draw a horizontal line at negative 1 on root 2. Negative 1 on root Where's the root? There it is, root 2. So if you imagine what that would be, well, you can just find the x values at those spots, either through the graphing tools, or you can literally just say where does sine equal -1 on root 2, which is actually there are exact values for that. That's all right. That's the first thing we can consider, right? You can imagine a preliminary domain would just be from, let's say, here to here, right? That would be one decent domain. But we also have to consider the other function, right? We need to consider the logarithm. So let's draw that logarithm. Natural log of x plus 1 on root 2, 1 on root 2. And from there, we need to make sure the range caps out at 5. So if I draw y equals 5, I'm going to have to change my domain to be significantly bigger. My window size, rather, to be significantly bigger. Look, even at 100, it's not even going to reach there. So realistically speaking, this is not going to be the bottleneck, right? This is massive. So it's just not going to reach there in any time soon. So really, we just care about everything from here, even like everything on this window is fine right now. The domain that is given to us, capping out at -1 on root 2, that's cool. We already know our lower bound, because -1 on root 2 is here, and, well, let's even see. How far is -1 on root 2? Menu 3, 2. To do a relation, just do x equals -1 on root 2. And you can see that caps out there, which honestly looks like an intersection there, oddly enough. If we zoom in, how far is that going to be? Yeah, it's a bit further up. So if I just zoom in a little bit more, let's say -5 to, I don't know, -1. -6, 7. Where'd it go? Oh, right, -1's too far. That's what the issue is. -5, -0.5. Oh, 0.2, whatever, doesn't matter. Huh, that might just be the cutoff point. Interesting. Zoom in even more. -2. Oh, it's so close, but it's not quite. Anyway, point being, -1 on root 2 is a little bit further than the crossover. Crossover's here, -1 on root 2 is here. And we can prove that by just solving it, right? Where is sine of x equal to -1 on root 2? Comma x. Just to limit the domain a bit, I'm going to do from -pi to pi, just so we don't get a million different answers. -3 pi on, or -pi on 4 would be that spot. So if you control enter on that, and if you control enter on -1 on root 2, you're going to get a surprisingly close estimate here. This number is indeed smaller than this number, hence, well, I mean smaller in magnitude, it's closer to the origin. So this one is slightly right of this one when you look at the graph here. So since that one was further along, that's going to be our lower bound, the -1 on root 2. So new domain has a lower bound of -1 on root 2. And the upper bound of that domain is just going to be whatever the cap was for the sine. So if we expand this back out to some normal numbers, it's going to be this cap here, wherever that ends up being, which would be, let's expand this out to 2 pi just so we can see a bit further. Probably the 5 pi on 4. Let's double check. If I do x equals 5 pi on 4, I should get here. X equals 5 pi on 4. Yeah, so it's going to cap out at 5 pi on 4. So let's look at our answer set. -1 on root 2, 5 pi on 4, answer A. Okay, moving on to section B of the exam, starting with question 1A. So we're simply told to state the coordinates of all of the axial intercepts of f. Now the good news about this is that we're given f of x in its factorized form. And so we can very quickly see that all of our x-axis intercepts are going to occur at x equals 0, x equals 2, and x equals -1. Now, don't give those specifically as answers. It is asking for the coordinates of the axis intercepts. So you would instead do 0, 0 as your first coordinate. Then you would say 2, 0. And you could also say -1, 0. That's all that's required for this one. Okay, on to 1b now, which is finding the coordinates of the stationary points instead. So, only real difference here is that we're finding a derivative approach. Basically, we're going to do our derivative and then set that equal to 0, and that's going to find all the stationary points of our function. Reminder, this is tech active, so we can use our CAS for that. So if we go through, go menu 3, 1 for solve, shift minus to get the derivative up, ddx of x times bracket x take 2 times bracket x plus 1. And we set all of that equal to 0, and we want to know the x coordinates at those spots. And in this case, you're going to have plus minus some root term in there. So to find the corresponding y coordinates at those spots, all you're going to do is sub those into our function. Now I'm going to quickly define that as a function. Just define a of x as specifically the inside of here. And then once we do that, we can safely sub in our x values. So I'm going to do a of, let's just do the second one because it's easiest to, well, I guess I've copied the whole thing instead. That's fine, we'll just delete the things that we don't want. That's going to give us a coordinate like that. And all we would have to do from here is chuck a negative sign on this. And that would be the coordinates for our points. So you'd have, that's the x, that's the corresponding y. That's the x, that's the corresponding y. Alright, part CI is going to be nice and quick. We're just trying to find where f of x is equal to g of x, specifically only the x values. So I've already defined f of x as a of x, so maybe we'll do a nice little rewrite of that. We'll just rewrite f of x, and we'll call it specifically this part. So we'll grab a copy of that, rewrite it just so it's a bit clearer what we're doing. And then g of x, well, if we call our new function g of x, it's going to be x minus 2. All we would do from here is simply put it in a solve. Where does f of x equal g of x, comma x? And there's our answers. Plus minus square root of 5 with the plus a half as well, and the x equals 2. You just write all those answers down, and that becomes your answer to part CI. Alright, a bit more challenging now with part CII. We're trying to find an expression using definite integrals that'll give us the area bound by those two functions. So before we can really do that in any meaningful capacity, we should get an idea of what our graph looks like. So we can plot f of x and we can plot g of x and see what the bound area even looks like. So g of x, and we can see that it slices through somewhere in the middle where you're going to have this sort of bound area in here and this sort of bound area in this little bit as well. We want to know the areas for both of those. Well, okay, how are we going to achieve that? Whenever you're doing bound area for anything, you need to do an integral of top take bottom, basically put. So if we just quickly rewrite what a generic area equation would look like, it would be the area that is bound will always be the integral from start to finish, whatever the x domain is, of whatever function is on top minus whatever function is on bottom. And that would be the area for that specific section of your graph. So if we're thinking about what we would have to do here, we would have to have an integral of top take bottom for this section here, so from this intersection to this intersection, and we would also have to have the exact same thing for this intersection and this intersection here, two individual bound areas. How do you do that? Well, we've already actually found these x coordinates that are associated with those intersections. That was the solution to f of x is equal to g of x. So we use those answers to say, well, okay, it's between here and here. That's our integral domain. All that's left to do is figure out which function is on top and which function is on bottom for that section. And in this case, the red line, f of x, is above the black line, g of x. If it's above, it's considered to be the top. Similar can be said about the second domain, except the black, the g of x, is now the top, and red, the f of x, is now the bottom. So all we're going to do is make use of that. Going all the way to the beginning, apparently too far to the beginning. Where, oh where is the actual, must have been, yeah, there we go, 1.4. So these are the coordinates that we have to split our domain up in terms of. I would almost control into that just to make sure that you're hitting the right ones. So first domain is going to be these two. So we're going to do our shift plus, and well, I guess we don't have to actually solve it quite yet. That'll be the answer to triple I, but we can at least have it written down on the CAD as well, and then just copy that down at the end. So lower bound is going to be the first x coordinate. So Control C on that, Control V all the way down here. And then exact same thing, but our upper bound is now this one. Control C, Control V. Now we do our top take bottom. So again, referring to our graph, f of x was above g of x in that region. So we'll do that. We'll do f of x take g of x. Put our dx in there. And then we just got to add that to the area of the second section. So the lower bound will now be this one here, because that's where we left off. And our upper bound will just be 2, I believe. Was it 2? It was 2. Not going to bother copy pasting that, that'll take too long. And once again, if we refer to the graph, now g of x is on the top. So we're going to do g of x instead as the beginning, and then f as the final one. So we do g of x, take f of x. Dx. I'm going to hit Control Enter because triple I did say to do it to 2 decimal places. And as for what we write in as our answer to double I, writing the expression down, you're just going to write exactly what I've done there. Right, it's just going to be, that's your lower, that's your upper. Even specifically write f and g, just so you don't have to write too many things. And then the exact same thing. You're going to add the integral here, and that'll be all you need for double I. Okay, so here's where things get just a little bit trickier, specifically with part D over here, where we are told that h of x is basically equal to a changed version of f of x, where f of x was that previous cubic that was in its factorized form. If we take a quick look at what h of x is, it's a linear term multiplied by a repeated linear term. So basically that tells us that we have an axis intercept at x equals a, so it cuts through at x equals a, and we have a turning point on the x-axis at x equals b. Right, that's what it means when you have a repeated linear term. So that's the format of what h of x can be. That's all it's ever going to be. So we need to figure out what do we have to do to f of x to make it look like that. Because if you look at the current f of x, if we just sort of go back a step, f of x is that red one there. It's not really getting what we wanted, right? There is no, well, for starters, there's 3 axis intercepts there. But what we wanted, ideally, was to have 1 axis intercept and 1 turning point. Now, if you imagine that k term there, that's a vertical translation. And so basically what that's doing is just sort of shifting your graph up and down. And the idea is to try and figure out, well, okay, what would it take to shift it up so that we do have a turning point on the axes, or perhaps instead shifting downwards? Because if we go ahead and define h of x as equal to f of x plus k, as equal to f of x plus k, and we go ahead and plot what that would look like with a slider. So f of x, wait, sorry, I already did that one. We'll do h of x. If we then just sort of drag this slider around, we'll see that as k gets larger, it shifts upwards, right? It's a vertical translation. And so we need to figure out, well, okay, how far do I have to shift this up for this turning point to touch on the axis? And the good news is we actually already know the answer to that. So if I deselect that and actually, yeah, there we go. Now I can navigate. We already figured out the coordinates of our turning points earlier. We did that all the way back in part B. We found the coordinates of the stationary points. So if we know the y values of each of those stationary points, all we have to do is shift up or down by that value and it will touch the axes. So if we go ahead and go back to figuring out where those were these y values here, right? So if I were to set k equal to this, for example, it would have to be, because that would be a positive, so we need to set it to the negative of that to shift it downwards. So if I were to set k equals the negative of that, so it goes downwards, then when we go back to our graph, we should see that it's on the turning point, then it's on the axes, which of course it is. That is one possible k value for this situation. The other alternative was we had, instead of shifting up, we can shift downwards. So again, if we go back and have a look at the possibilities, we had a negative y value that we can shift upwards instead. So if I were to define k as the positive of this, define k as the positive of that, then once again we see that we've achieved what we wanted. So how does this help us? Well, whatever this coordinate, this x coordinate now is our value for b, right? Because the x coordinates don't change when you go vertically. That's never going to change. So whatever this x coordinate was is now a possible value for b. And the alternative is true for a different value of k, right? That would be, if I grabbed this one, then whatever the x coordinate was there is another possible value for b. So if we go back and figure out what those x coordinates actually were, all the way back at the beginning, then these are the possible values for b, right? With the plus minus root 7 plus 1 all over 3. So let's write that down. So one possible value of b was the positive root 7 plus 1 over 3. And the other possible value was negative root 7 plus 1 over 3. Now all we have to do is figure out, well, okay, what are the corresponding a values to those? Because we don't just care about the turning point, we also care about where it intercepts as well. So the current one that I have here, if we go all the way here, the y-intercept is over here. Now we do need an exact value there, so we do need to solve this actual equation. So if we go through and actually solve that, what is the x value? Well, basically you're just solving for h of x equals 0 is fundamentally all we're doing. It's doing h of x equal to 0, comma x. And sure enough, we're going to get the one that we expected, which was the b value. And then you're going to get the corresponding a value that comes with that. So that was the negative root 1. So that would be this possibility here. And so you could then say a that corresponds to that would be 2 root 7 plus 1 all on 3. If we then redefine k as this and then solve again, well, we're going to get possibly what we already expected, which is the negative side of that root. So corresponding to that would be negative 2 root 7 plus 1 all on 3. And we should say a is equal to that. And if you outline your solutions like that, you make it clear that those are individual possible pairs. That'll be your 4 marks. You could do like a keyword or here, this or that. That could make it even more clearer. Anything you can do to basically make sure that you understand that those are dependent on each other. They can't just be mixed and matched any odd way. Okay, question 2 now. So this is an example of a circular functions thing. You can pretty much already immediately tell that, not just because there was a circular function given, but also because there was a Ferris wheel given, right? Anything that moves in a circular motion or is periodic in nature is going to be a circular function thing. But okay, all we're told to do is figure out what B and C are, or at least prove that B and C are what the exam says it is. So let's have a look. B is the stand-in for the end term, which is, related to period, and C is the stand-in for the vertical translation term. So the easiest one probably to start with is typically going to be the vertical translation, right? Because you can kind of just get that from the measurements. So we're told the height, this is a function for the height of the carriage, what do they call it? A pod. It's going to be the height of the pod as it goes around that circle. And so if you think about like where the absolute minimum and maximums are, well, this is as low as the pod can be at point A here. And from there, it's only going to get higher and higher and higher until it crests, until it peaks at here, in which case it'll continue to oscillate between that peak and trough. Now, we're told the absolute minimum there is 15. We're also told that the wheel has a radius of 60 meters. So that means that from point P to point A is a distance of 60 meters. So, okay, that means that our absolute minimum is 15. This is 60 meters above that, so 75, and then the peak is 60 meters above that. Now, the key with the vertical translation is to identify that, well, recognize that the vertical translation will always be the mid-level of your circular function. So if this point P, point B, anything along that horizontal line, if that is your midpoint, then that means that C must be 75. And, we kind of see that already with the show that. So the kind of working that I would expect you to put there would be to say something to the effect of C is equal to 15 plus 60. That'll be fine. And then as for B, well, we mentioned that was related to the period, right? Because period is 2 pi on n, where n is in the spot that the B is currently occupying. So how do we figure that out? Well, there will always be some information in here that will tell you what the period of your scenario is. And in this case, we're told that a full revolution is completed every 30 minutes. Well, that means that our period, capital T, is equal to 30 minutes. Period is also equal to 2 pi on n, but in this case our n is a B term, and so all you do is rearrange to get the B on its own. Or you just solve this in a CAS, but this isn't too bad. Right, you've got 30B equals 2 pi, B equals 2 pi on 30, B equals pi on 15. Okay, this one can throw you off. So part B says find the average height of the pod as it travels from A to B. Now that's pretty important there, A to B. All right, we kind of talked earlier about like the mid-level of a circular function. That's different to the average height, specifically because it's going from point A to point B. Right, point A to point B is not a full revolution. So you have to use a very specific, different type of formula. As soon as the word average comes into play, as soon as you see a word like that, your first thought should probably just be average value, right? Using the average value equation from integrals. Correct 2 decimal places also should give you an estimation to say, well, maybe it's going to be an integral thing. So how do we actually do the average value of anything? Well, we need to know the start and end. That's our B take A. And so we'll do, just so we can have it like written out, it's 1 B take A from A to B of your function, f of x, whatever that is. Right, that's pretty much how you would do the average value of any function. So we need to figure out, well, okay, what is our boundaries? What is this function? Well, this is a function of time. This is h of t, h of time. So when we think about our quote-unquote x coordinates, we're actually thinking about time values. So we know that this starts at A, right? Starts at the lowest point, A. So what that means is our initial coordinate, a lower bound, is going to be time equals 0. But how do we know how long it's going to take to get till B? Well, that's where the period comes into play. If it takes 30 minutes to do a full revolution, then it's got to take 15 minutes to do a half revolution, it's got to take 7.5 minutes to do a quarter revolution. So our upper bound is going to be 7.5. So we'll put a 0 here, 7.5 here, and then all we're going to do is plug in what our function actually is, which is, of course, -60 cos bracket b, which we know is pi on 15. Pi on 15, whoops. B. You can do x, you can do t, it doesn't really matter as long as you're consistent with it, with like the dx at the end. Did an extra couple set of brackets, but I guess that doesn't matter too much. And then plus 75 there. Control instead to give you 36.8 meters. Don't forget to actually give the answer in meters there, right? So you do 36 point, well, I guess it's 2 decimal places here, isn't it? So it would be 36.80 specifically. In terms of meters, just do a double check to make sure that actually makes sense for the scenario. If 15 meters is here and 65 meters is here, then yeah, I suppose, and 75 meters is here, we can say, yeah, 36 is approximately what we're looking for. This one is a little bit more straightforward than the previous one. So part C, we're trying to find the average rate of change. So average rate of change is a very specific keyword. There's only ever going to be one way of doing that, and that's going to be your effectively your rise over run type thing. So since we'll be writing out the function a couple of times, I think what I'll just do now is just actually define what that function is. Grab a copy of it, which is all of this. Control C, Control V. And now average rate of change is always just, as I said, the rise over run. So it's h of A take h of B over A take B, or I guess it's the other way around, right? B as our upper bound. So you just need to figure out what are those spots. Well, we already knew the upper and lower bound. We've done that before, so there's nothing really too special to be done here. H of 0, 7.5, take 0, Control Enter, and that's going to give you 8. So specifically, you would write 8 meters per minute in that case. Okay, moving on to something just a bit harder now, which is DI. We're starting to look at transformations. We need to figure out what is K and what is M. Well, let's have a look at where those things are situated. K is right here, and M is right there. So K is a constant value, and M is a coefficient on T. Fair enough. So what's the actual situation here? What are we dealing with? Well, we're told after 15 minutes, the wheel is going to stop moving and remain stationary for a further 5 minutes. And then after that, it's going to double its speed. This new function that we have here is the new function that describes the height of the pod with this new scenario. So we can see it kind of matches up, well, it exactly matches up to what the scenario was saying. For the first 15 minutes, nothing has changed. It's still just h of t. Then for the next 5 minutes after that, we've got a constant value, k. Makes sense because it was stationary at that spot. So if we want to know where k is, or what k is, we basically want to know what height did we reach before we started going stationary. Well, we know when we got stationary, which was h of 15, right? The height value when t was 15. So if we just do h of 15, we can pretty safely say that k is going to be 135. So that's k. How about m? It's a little bit tougher there. So if you think about what that actually would look like, h of mt plus n, m is a coefficient on t, so you can think of it as impacting the period of the circular function. And so that also makes a bit of sense because we expect the speed to double for that final duration. Now, if the period is how long it takes for a circular function to repeat once, or in this case for the journey to repeat once, then doubling the speed means it should take half the time. So the period should be halved. We need to figure out what value of m do we choose to make sure that the period gets halved. Well, it's a bit trickier than just assuming that m should be half of what b was. What we should do instead is see what actually happens if we plug in that transformation. So we put in our mx plus n. What does our function actually look like now? And so we've subbed in our value, and we see that now the coefficient on the t, in this case I've written x, is m pi over 15. Well, okay, what we need to do now is figure out, well, okay, what do I have to do to this to make sure that the period is half of what it was before? So if you go back, you see that the period was 30 minutes, so we want the new period to be 15 minutes. So that means that we want 15 to be equal to 2 pi divided by, well, the new n term, which is just all of this, m pi over 15. M pi over 15, dividing that. Now, that can be a bit complicated to do by hand, or at least you wouldn't really want to risk doing it by hand when a calculator is available. So we're just going to do a solve. 15 equals, you can even do it as fractions if you want, 2 pi divided by bracket m times pi over 15. Solve that for m, and we get m equals 2. So to summarize, we have m equals 2, and we have k equals 135. Okay, and then to cap it off, DII, find all the possible values of n. So the good news about that is that n is now the only unknown in our equation, right? We know what m is, and we know what k is. Now, interestingly enough, the only thing that actually matters is the m value in this situation, because we're only going to be using the third part of our piecewise for this. So if we go ahead and have a look at h, where m is equal to, m is equal to 2, then our new function looks like this. All right, that describes the section of our the section of the ride that is double speed. Now there is an n in there, right? We've got the n pi over 15 there. There's also an x, and there's also a an unknown y. So as long as we're able to sub in a point into this equation, we'll have n as the only unknown in that equation. The question now becomes, what point can you sub in? Well, the good thing about this kind of function, the piecewise, is that it has to be continuous. Otherwise, it's not going to make much sense for the Ferris wheel. It would have to sharply change, which it certainly will not do. What we do know is that the height, as soon as this function 3 takes over, is going to be exactly the same as the height from where it left off, which we know is 135. So we know the y value is 135, and we know the t value at that spot is 20, because it's time equals 20. So if you were to solve that, 93.1, 135 is equal to h of, now we've got to be a bit careful here, so it will be 2 times our x value, which is 20, and then plus n. If we then solve that for n, then we're going to get our general solution, right? We're looking for all the possible values of n. If we quickly double check, we see that n can be an element of all real, which means we can very safely say that n is n is equal to 5 times 6n plus 1, right? You would just give exactly that. You wouldn't say n4, though. You would just replace that with n. So as a final answer, you might write n is equal to 5 bracket 6n plus 1. You could expand that out if you want. Leaving it factorized is fine as well. And then finally, we're just sketching the graph of the piecewise. That will not be difficult because we have access to a CAS. So really, all we're doing is defining the piecewise. So we could say, what do they call it? They called it w of x, didn't they? So we'll call this w. We're going to hit the button right next to the book, and then this button here. Now, we know there's 3 pieces to that piecewise, and so what we're going to do is plug in exactly what we see here. So the first thing is going to be h, and that's going to be from 0 to 15. So 0 less than equal to x less than 15. Then we're going to have k, which we know was 135, which is from 15 less than equal to x less than 20. And then finally, you're going to have h of bracket, so m was 2, so 2 times t plus now n. What's going on there? So you can pick any value of n. the reason why any is acceptable is because circular functions repeat, right? So all it's doing is saying, well, okay, instead of getting this peak, you're now getting this peak that's further along. So we can just pick one of those values of n. If you look at the possibilities here, if, oh, that's actually a bit weird. Yeah, if you hit n equals 0 on this, you're going to have a possibility of actual n, the coefficient n, is equal to 5. So if we've got a plus 5 in there, then we can finally say that's from 20 less than equal to x less than equal to, what's the final? 27.5. 27.5. And then finally, if we plot that on a graph, w of x, we're going to have exactly what we... Oh, I made a mistake there. I should have put t. Where is it? Yeah, instead of putting t there, that should have been an x. My mistake. There, hit enter, and then we're just going to resize our window. So we know this is going to be at least from 0 to 30, sounds about right. And then we know it can't get lower than 0, and it can go up to like 140. And so that's going to be our graph that we copy. We can give ourselves a bit more room for error by just doing like, I don't know, let's say -2, just so you can see the graph a bit more clearer. But all we're doing is drawing that. So making sure that we have the endpoints, that's a big thing. So you want to know where's here and where is here. And then, yeah, just hitting the right y values. So this y value here is 135. So when you're drawing it on this axis specifically, you're putting it about where my cursor is here, where the cursor is there. So that's going to be your flat bit that's in the middle on the CAS. And all you're doing is matching the curve at that point. So very quickly we can figure out what are our endpoints. So if I put w of 0, we should get 15, because that's what the question told us in the beginning. It starts at A. And then if we do w of 27.5, don't actually know where this will be. No, okay, yeah, makes sense. 15 again. So you would have to do that about here on the cursor. So along that line midway through would be where you label those endpoints. As for the t values, so making sure that you cross over at the right spots. Anytime, once it goes like flat here, that's going to be from t equals 15 to t equals 20. So you would do your flat bit from here, 15 to 20. So this bit here would be flat. That's all. Okay, next up, part 3a. This is possibly about as easy as it could get. State the value of the limit as x approaches negative infinity of g of x. The reason why I say it's basically as easy as it can get is because even if you don't know what it is saying, all you ever have to do is define g of x and literally plug that in exactly to the CAS. So, when you want 1, g of x is equal to 2 to the x, 2 to the x plus 5. And then all we do is plug in our limit. So limit can be found under the calculus menu. Limit number 4, x approaches negative infinity, g of x, And then you just say that your answer is 5, which makes sense. So when you think about what that exponential actually is, it's 2 to the x, so it's a positive exponential. It goes to the right-hand side. Should probably zoom in so you can actually see what's going on there. 2 to the x is a positive exponential, so it's shooting off to the right-hand side, and it's shifted up by 5, meaning that your asymptote is going to be at 5. So if you think about what that looks like on a graph, as you get closer and closer to negative infinity, you're going to get closer and closer to y equals 5. Right, if I draw the line y equals 5, you'll see it very quickly approaches y equals 5. Hence, that is the value of our limit. This one is also not so bad. It's just what is the derivative of g of x. So, once again, we can just go in and tell the CAS to do that for us. d dx of g of x is going to give us natural log of 2 times 2 to the x. So we specifically want to find k under this circumstance, where k is the coefficient on our exponential 2 to the x. Under these circumstances, that means that k is equal to natural log of 2. Apparently this is the part of the exam where we pick up all of the free marks. So in this case, we're doing CI, let a be a real number. Find, in terms of a, the equation to the tangent, or of the tangent to g at that specific point in terms of a. Well, the good thing about this is that the CAS has a tangent line function. It's found under the calculus menu once again, all the way down here at 9. So we want to find the tangent to g, so the first thing we're going to do is put g of x as our first operator. Then from there, we want to find it at an x coordinate. Specifically, that x coordinate is a. Now I can't do that immediately because it's bolded, so it's going to have an issue with that. So all I'm going to do is clear what a was. So if I delete a, redo that again, and we're going to get some really nasty thing. But that is the equation of the tangent. You would write exactly that out word for word and enjoy copying that down. Now here's where things get just a little bit trickier with CII. Hence or otherwise, so that means that our previous answer is going to be important. Hence or otherwise, find the equation of the tangent to g that passes through the origin. Correct to 3 decimal places. So passes through the origin doesn't necessarily mean that that point exists on g, but it does mean that it exists on the tangent to g. It's an important distinction here. So if we want to find the equation of that tangent line, what we have here as our answer to the previous question is a generic tangent line taken at any x value of a, right? So if you see what CI was all about, it said, what was the tangent at this point? Now, the point was unknown, but the point being is that if you're subbing in any known point here, then all you're basically doing is replacing a with that x coordinate that you wanted to find a tangent line at. So, for example, if I wanted to find the tangent line at x equals 2, then all of those a's are going to be replaced with 2 if I just put a 2 in there. That's not quite what we wanted. What we want to know is figure out, well, okay, what value of a do I have to pick such that I will go through the origin with that tangent line? Well, this right here is a function, right? You can imagine this as just some generic tangent line function. If we know that it goes through the origin, then all we have to do is replace our x and y with 0, 0. And that'll give us the, well, at least the a value that we care about. So if we go ahead and do our menu 3.1 solve, we set the y value to 0 and we set the x value to 0, which is this one here. Set that to 0. And all we're going to do is solve that for a. And that's going to give us a is equal to that. That did not come out super well, did it? Equals 5. What's going on? Got a control into that, do I? Yeah, there we go. That's a bit better. 3 decimal places, that's fine. Now, the answer to A is not what we're trying to get. We're trying to get the tangent line. So, realistically, what we want to do is sub this A value into our tangent line equation, which means defining it, first of all. So, let's say O of A is equal to that tangent line function, and then all we have to do from there is simply sub in what A actually, whoops, I hit that a bit too early. Go away, click that A, control enter, and that's going to give us what the tangent line is. So you can see we have a linear, makes sense, right? We've got some coefficient of x, and we've got some constant. Now, writing this to 3 decimal places just means that we're just looking at this x thing here. Like, this is really small. This is 2 to the negative 13. That is just 0. So what you would have as a final answer here would be 4.255. 4.255 is 3 decimal places. So you would finally have tangent line, so you can call this whatever you want. You can be very specific with it. Tangent equals 4.255x, and that's really all you'd have to do there. Okay, we've got something a little bit different here. Still a 1 marker though. Find the coordinates of the point of inflection. Now, there's a couple ways you could do this. The way that I'm personally going to recommend is that you just sketch h of x and then use the graphing tools to figure out where the point of inflection is going to be. So if we go ahead and do that, we have to start by defining h of x. So many11, h of x is equal to 2 to the x minus x squared. 2 to the x minus x squared. From there, we can just graph h of x, and then just physically observe where the inflection point is. And the inflection point is going to be that there. So with that in mind, we need to just figure out what that spot is. And if we go through our graphing tools, we will see there's an option for inflection, in which case we just highlight over that and grab that point. Now I believe this is 2 decimal places. Yeah, 2 decimal places. So we'll simply just want to do 2.06 and negative 0.07. So that would look like 2.06 comma negative 0.07. That's what you would give as your final answer for the inflection point coordinates. Alright, part E. Where is h strictly decreasing? So again, the graph of this can be quite nice to have access to, just to quickly observe where are we strictly decreasing. The graph is strictly decreasing. Let's try that again in English. The graph is always going to be strictly decreasing during the interval where it's going downwards. So you can imagine the only spot that's going downwards is from this turning point to this turning point here. So we just need to find those turning points, correct to 2 decimal places. Now, easiest way to handle this would just be derivative equals 0. I wouldn't even bother going through the graphing tools on doing that because it's a bit unwieldy. So we're just going to do many31 solve shift minus of h of x is equal to 0 comma x, and then the answer to that will be the interval that you give. So in this case we are going between, in 2 decimal places, that would be 0.49 and it would be 3.21 for your x values. Don't forget to use your square brackets. You want to use square brackets because it's got to include those turning points. It strictly decreasing simply just means the y value immediately after it is lower, and so you want to make sure that you're including those turning points because those spots are in fact lower than where they were previously. Okay, part F for Newton's method. So if you already defined how Newton's method works in the calculator, then you'll be nice and happy because all you have to do is replace a of x, or whatever you defined as your function for Newton's method. All you have to do is repeat whatever that definition is. For those who haven't already done that, or if you're just skipping around in the video, then my recommendation is that you set up Newton's method as follows. So you start with your a of x, which is going to be whatever function that you are trying to use Newton's method on. In this case, we're using it on h of x, so I'm going to just immediately define it as h. From there, you want a second function, which is always going to be defined as the derivative. So derivative of a of x. That's how it's going to work. And then the final thing you do is define your, whoops, that's not what I meant to do, many11, you define your Newton's method equation. Now I'm just using a, b, and c. You can use whatever you please. But what you're going to do is actually define a Newton's method here, where Newton's method is just x take the fraction of a of x over b of x. And just so you can see exactly why that is, if you look at the definition of Newton's method, you've got xn, you've got f, and you've got f dash. F is the function we care about, f dash is its derivative, and well, you see the x minus, which was already discussed. Okay, so once you've defined your Newton's method, all you're going to do is sub those points in. So we're starting with our x equals 0. Right, we're told we're starting with x equals 0. So the way that works is you just do c of 0. And specifically we're trying to do this to 3 decimal places. So the answer that you're going to give for x1, your next guess, is going to be, well, this thing here, negative 1.443 in this case, since the 6 will cause it to round. So the answer for x1 is going to be negative 1.443. Now from there, to get the next guess, you're just going to feed in the previous guess. And that's going to give you, in this case, negative 0.897. So no rounding required there, it's already rounded. And then lastly, you're just going to give feed through again, negative 0.773. Again, no rounding required for that one. Alright, part G is a bit of an interesting question. It actually requires you to understand how Newton's method works. So it asks us to explain why we would not use a solution to that equation equaling 0 as our initial estimate. Well, to figure out why that might be an issue, let's see what those solutions actually are. So if we solve what that is, solving natural log of 2 times 2 to the x minus 2x equals 0, comma x, if we see what those solutions actually are, we get 0.485 and 3.21. Now, do those sound familiar at all? If we keep going back, oh, look at that. Those are the same solutions to when the derivative is equal to 0, which is our turning points. So the question now sort of simplifies to, why don't we want to use turning points for our Newton's method? Well, if you know how Newton's method works, you basically are doing, it's another word for like the gradient descent method, where basically the way it works is that you take repeated tangent lines over and over again until you get closer and closer to an x-intercept. So for example, if I took a tangent line, let's say here, it would intersect approximately at where x equals 1 there. If I then took another tangent line at x equals 1, it would get closer and closer and closer until eventually it hits the x-intercept. If I take it at a turning point, I've got a perfectly flat line. Right, that's not good. And so if I have a perfectly horizontal line, it's not going to touch the x-axis anywhere. And because of that, Newton's method will break. So the summary there is, the explanation rather, would just be Newton's method does not work if your tangent line is perfectly horizontal. That's the gist of it, really. Okay, welcome to the worst part of the exam, part H. We're told that there is a real positive number of n for which f of x has a local minimum on the x-axis. Now, I've tried a bunch of ways to do this purely on the CAS. A lot of the times when you try to solve things, it just really doesn't end up working out all too well. Some things that might come to mind would be f dash of x is equal to 0. Right, we have a local minimum on the x-axis. Local minimum should be pretty related to derivative equals 0. It's a turning point. The other thing you might consider is that f of x is equal to 0 because, well, if it has a minimum on the x-axis, then it has to cut, or at least touch, the x-axis. That's actually how we're going to start this one out. It ends up being the case that solving this analytically, for the most part, so by hand almost, tends to be one of the better ways of going about it. So if we know that f of x is equal to 0, we have 0 is equal to n to the x minus x to the n. What that tells us is that x to the n is the same thing as n to the x, right? Just by chucking that to the other side. These are equivalent. Now, the only way this is going to be equivalent is if x is equal to n, right? That's like the only real solution there. As long as x and n are the same thing, then this equality will hold. So that's important to understand there. X is equal to n. The next thing worth considering is f dash of x should be equal to 0, like we said, right? But if we know that x is equal to n, we can replace x with n. So if we go ahead and define our f of x, so many11 f of x is equal to, oh, why did x go bold? Let's get rid of that. Delete variable x. If we redefine f of x, we're going to have f of x is equal to, it was n to the x, n to the x minus x to the n. So we've defined our f of x. We can now move on to defining its derivative. So I'm just going to call that O of x because why not? Define O of x as the derivative, as equal to the derivative of f of x. So if we have a look at what O of x actually is, then we can see that. Now, crucially, x is equal to n for our specific criteria here. And so one thing we can do is replace all of these x's with n's. So if we go ahead and actually do that, what we're going to get is natural log of n to the power of n minus n times n to the n minus 1 is equal to 0. Now we can bring this n into here. Going to have natural log of n n to the n minus n to the n, because when you multiply by the same base, you just increment the power, and that has to be equal to 0. Well, okay, n to the n is a common factor here. We can take that out the front. N to the n, bracket, natural log of n take 1 is equal to 0. Now, n to the n equals 0, that's not going to have any solutions, right? That doesn't make a whole lot of sense there. Even if n was 0, then you would have 0 to the 0, which is undefined. So we can ignore that bit there, and we can just focus on natural log of n minus 1 is equal to 0. That's going to give us natural log of n is equal to 1, which can only happen if n equals e. Because when you have same base and bracket, your logarithm will equal 1. Okay, on to some probability stuff. So, we are told this is a normally distributed random variable, and it has a mean of 6.7, standard deviation of 0.1, and we're simply just trying to find some probability. In this case, d is greater than 6.8. Anytime you're trying to do probability with normal distribution, you would use the normal CDF type function. So you go through your menu, finding the probability, distributions, and then number 2, normal CDF. We set our lower bound to 6.8 since we want to have everything that is greater than 6.8. We set our upper bound to infinity. Mean was 6.7, and standard deviation, whoops, there we go. And standard deviation was 0.1. Hit enter, and that is our answer. So for 4 decimal places, we're going to have 0.1587 in that case. Okay, slightly different here. This time we're trying to find the minimum diameter of the tennis ball such that it is larger than 90% of all tennis balls produced. So what is the smallest value such that 90%, it is larger than 90% of them? So if you think about your normal distribution, what that might look like, it's some sort of bell curve looking thing here. So if you want to be bigger than 90% of everything, you kind of want to know what's this value here, right? If everything here is smaller than it, you're bigger than 90% of all of that. So the way that works is using the inverse normal function. So same spot on the CAS under distributions, but it's going to be number 3 here, inverse normal. Area is just how big you want everything to, how much you want it to beat. So you want to beat 90% of the total possibilities, so you want your area to be 0.9. Mean and standard deviation, they're not going to change. 6.7, 0.1, and that's going to give us a diameter, so in centimeters, yes, centimeters to 2 decimal places. Centimeters to 2 decimal places would be 6.83 in this case. Okay, part C. Find the probability that the tennis ball will fit through the opening at the top of the container, where the top of the container has a diameter. Well, a tennis ball can fit in there as long as it's smaller than 6.95 centimeters in diameter. So again, this is kind of a probability thing. You want to make sure that you want to have your diameter less than 6.95 centimeters. What's the probability of that occurring? So 6.95 becomes an upper bound now. Menu 553 in 2 rather. Lower bound is now infinity because it can be as small. Now, technically, you know, in real world, you would set this as 0, but when you use normal distribution, you always have your upper and lower bounds as infinity if they are unbounded, regardless of what makes sense in the real world. But okay, as for our upper bound, it's 6.95. Mean 6.7, standard deviation 0.1. And just like that, we would have a 4 decimal places, find the probability. We got a 99.38% chance. Okay, part D, a little bit different now. Now we have a random selection of 4 tennis balls, and we want to make sure that at least 3 of them fit through the opening at the top of the container. So this is where we start looking at the chance where probability types can change from question to question. Under these circumstances, we've changed to a binomial. The reason why is because now we're looking at individual tennis balls. Does it fit or does it not fit? That's a binomial thing. It's either succeeds or fails. And we are also somewhat implied that everything is independent, right? We know that the probability of any tennis ball being a certain diameter is given by a normal distribution. It's not dependent on the other tennis balls in the batch. So under these circumstances, we are binomial. So for binomial, we want to know how many trials, how many successes, and what's the probability of a success. In this case, we'll consider a success to be fitting through the top of the container. Funny enough, we already figured out what that probability is of that thing occurring. That was the previous question, the probability that we fit. So we can use the probability from before as our p-value for binomial. We want to know a range of successes, at least 3 balls, so 3 or more out of the selection of 4. Hence, we're going to use a CDF. So binomial CDF, number of trials was 4, probability of success, we're just going to leave this blank for a second so we can copy and paste it over later. And then lower bound was 3, since it's at least 3. And then upper bound is going to be 4. Now, we're just going to delete that little placeholder and replace it with the actual probability, which is this one here. And it's going to give us, okay, how many decimal places? We need 4. So it's going to give us 0.9998 as a probability. Now for part E. So in this case, we now have a grading for our tennis ball, right? We are told that a tennis ball is classed as a grade A if the diameter is between those figures, otherwise it will be considered grade B. Now, as for the actual question, we're told, given that a tennis ball can fit through the opening, so that's our conditional, find the probability that it's classed as grade A. So, whenever we're doing any conditional probability, we have to start with the conditional probability formula. So the probability that we're looking for is grade A, so we're going to say PR, let's just call it A, given that it fits. So just for shorthand, I'll say given fits, like that. What we're going to do now is expand what that looks like, which means we need to know the intersection between those two things. PRA intersection fits divided by the probability of our conditional probability of fits. So we already know probability of fits. We found that one earlier in part, where was it? Part C, right? Find the probability of any tennis ball fitting. So all we need now is the intersection between those two things. What is the probability of being grade A and also fitting at the same time? So for grade A, we need to be between 6.54 to 6.86. To fit, we need to make sure that we are smaller than 6.95. So we need to be smaller than, so we can say fits is smaller than, so to the left of 6.95. The intersection of those two things is just going to be from 6.86 to 6.54. Right, that is the intersection. If you were to put these on a number line, you would see that a bit easier. So here's 6.54, here's 6.86, and here's 6.95. So probability of A just means this specific interval. Probability of fits means you want this. The intersection is that. So this is our intersection. So we need to find the probability of this occurring. Probability of A intersection fits. That's going to be a CAS thing. So what we're going to do is bust open the CAS and just plug those probabilities in with the correct figures that we need. Okay, so we have that. We had a mean of 6.7, standard deviation of 0.1. So menu 5, 5, normal CDF, because we're doing a range of values. We want to be between 6.54 and 6.86. As said before, mean was 6.7 and standard deviation was 0.1. And it's going to give you a value there for our intersection. So just for the sake of having it written down, I'll only write it to a couple of decimal places, but we're going to use the full figure, 0.89. right? That's going to be roughly our intersection. All we're going to do now is divide by the probability of fits, which once again we want to have the full figure here. So we're just going to recalculate the probability of fits. So 95.52 fits has to just be less than 6.95, so 6.95 is the upper bound, and we're just going to have those same values there, 6.7 and 0.1. That right there is our denominator. So we just do numerator divided by denominator, Control Enter, and we get our final answer there. Now, for 4 decimal places, that means that we're going to have an answer of 0.8960. 0.8960. So let's write that out. Probability of A given fits is equal to 0.8960. So part F is a bit of a trickier one. In this case, we want to make sure that 99%, or at least more than 99% of all the tennis balls produced are considered grade A. And we have to assume that the mean diameter of tennis balls remains the same, and we have to figure out what kind of standard deviation would be required to achieve such a thing. So a good way to get this started would be to draw a quick graph of what the normal distribution would have to look like for that to be a possibility. So we draw a rough normal distribution. The mean is still the same, so we still care about our mean of 6.7. We want grade A, so grade A meaning that we're between 6.54 and 6.86. We want this probability to be 0.99 or higher, which means everything on the other side is 0.5% either side, or less, depending on how far above 0.99 you are. So for us in particular, we need to figure out, where is it exactly? Find the required standard deviation. Yeah. So we're looking for a specific standard deviation, which means we're looking for that breakpoint there. So how does this work? This is where z-scores can come into play. So we have our equation z equals x minus the mean all over the standard deviation. So why does this matter? Well, we know what the mean is. We know what our x values could be. The only thing left to figure out is z and the standard deviation. If we can get z, then we can get our standard deviation. The good thing is we can get z. We're simply looking for what z value would cause everything to be left of this point to be equal to 0.5%. So how are we doing that? Well, we have the inverse normal. 553 inverse normal. So we just need to know what's the area, what's the mean, and what's the standard deviation for that thing. Now you might think, oh, we don't know the standard deviation. When it's z, we do, right? We know mean has to be 0, standard deviation has to be 1 for the standard normal. That's what allows us to figure out our z value without necessarily needing to know the normal distribution's standard deviation. So for the area, we are looking for 0.5%, which means instead of doing 0.01, we're doing half of that. So 0.005. And that is going to give us negative 2.57 for our z value. Now we could write that down, but fundamentally all we're going to be doing is plugging that into our equation, that z equation. So we'll grab a copy of that, going to equal it to, so x, where x was that 6.54, since that z value corresponds to this spot on the normal distribution. We need the same x and equivalent z, minus the mean, which we know is 6.7. So let's do that, 6.7. And standard deviation, I'm just going to call it x, just so we have something for the CAS to solve for. What we do there is Control Enter, and that's going to give us a standard deviation of 0.06. Now for us, we need 2 decimal places, so yeah, 0.06 is going to be the correct answer for that one. Part G is a bit of an interesting one. We don't usually talk about confidence levels that aren't 0.95, but in this case we are. So we're told that there was a random sample of 32 tennis balls that were taken, and a confidence interval was determined to be between this set of values here. We have to figure out what was the level of confidence that was given as a percentage. Now that's interesting. So one thing worth understanding here is how to even take confidence intervals to begin with. And fundamentally, we're simply just doing the following. So let's section off a little bit of space for us. Any confidence interval will be given by p hat plus minus the standard deviation term. So if we just make sure I don't get this slightly incorrect, let's check out where that is. So it's p hat plus minus z times the square root of p hat 1 minus p hat all over n. That's so the minus will be the lower bound and the plus will be the upper bound of our confidence interval. Okay, that's all well and good, but what do we do with that? Well, our lower bound is 0.73-ish. Our upper bound is 0.94-ish. So that gives us two values that we are equal to in this circumstance. We also know that n equals 32, so that knocks out n for us. N equals 32. P hat is always going to be the center of our interval. And so P hat is just going to be the midpoint between those values. So let's quickly calculate what that would be. Okay. So we got, really? It turned off the moment that I decided to put something in. 0.9493 plus 0.7382 all over 2. It's going to give us a midpoint of 0.84375. So 0.84375. Cool. So we have p hat, we have n. That's actually pretty much everything that we need. If we check back and look at our confidence interval, we need to know p hat, we need to know n, and we need to know z to get that. Now z is the key to solving what level of confidence we have. If you think of z, you know, the 1.96 for z being like approximately 2 standard deviations, this value is going to tell us what our overall confidence is going to be like. So we need to figure out what is that. Well, to do that, there's only one unknown there, so all we've got to do is pick either the lower bound or the upper bound to solve for what z could be. So let's achieve that. 3.1, let's say the lower bound. So I'm looking for 0.7382 is equal to p hat, which was this. We're going to do minus because it was a lower bound, minus z times the square root of our fraction. So p hat again, bracket 1 minus p hat over n, which we know is 32. We're just going to solve that for z. That's going to give us some square root number. What do we do with that? Well, that z value tells us the plus minus distance between the normal distribution, or at least the standard normal distribution. So we have our standard normal. Z are those two values there. If we were to just quickly control enter that, 1.64 looking to be about 1 standard deviation separated. 1.5 standard deviations, you'd say. So this will be your negative 1.64, this will be your positive 1.64. And we want to know what's that area there. We can solve that, again, using the CAS. We don't have to use approximation. In fact, we shouldn't use approximation. So, with that in mind, that's what we're going to do. So, we need to know, I'll grab a copy of specifically this, just to make sure that we have an exact value when we do our calculation. We'll go menu 552 for normal CDF. Our lower bound will just be the negative of that, and our upper bound will be the positive of that. Mean of 0, standard deviation of 1, because it is standard normal. Just hit enter, and we're going to get, 4 decimal places, so we're going to get 0.9000. No, it would be 0.8999 for 4 decimal places. 0.8999. because the 1 gets rounded down. Quickly jumping back in to realize that I did not quite read that as I expected. So we needed to give a percentage correct to the nearest integer, which in fact would mean that you give 90%. The 4 decimal places were for the confidence interval itself, not for the final answer that we needed. Okay, part H is nice and simple, even if it doesn't look immediately nice and simple. The function is sort of irrelevant here. The only thing that really matters is that we're looking to exceed 50 meters per second when I find the probability that occurs. And so as long as you're aware that speed is on the x-axis, because it often the variable of interest often is on the x-axis when it comes to continuous probability like this, then all you need to do is set your lower bound to be 50, since you want to be above 50. So what we're going to do from here is define that function first, because I have a suspicion we'll be needing to use it a bunch of times. I'm going to call it h of x, just because I always call things h of x. In fact, no, let's use the same terminology that's being used there. We'll do f of x. I won't use v, that'll be a bit weird. 1 over 6 pi times sine of square root of x take 30 over 3. Cool, that's our function. Now we're just going to do our continuous probability thing, which means we want to do our integral from, now we're doing 50 because that's our lower bound. Now we're going all the way up until, well, first let's make sure the camera focuses. There we go. Up until 3 pi squared plus 30. That's our upper bound. I'm just going to chuck f of x in there, and then that'll give us our answer. Once we control enter, we'll see that the probability is, well, how many, what do we need? 4 decimal places, so we need 0.1345. Yeah, 0.1345. Part I is another simple one. So we want to find the exact mean for our probability distribution. Again, doesn't really matter what the function is. The mean of any probability or continuous probability distribution is going to be x times f of x, the integral of that, over the maximal domain specifically. So instead of putting the 50 there, we're going to put the 30. We're going to have 3 pi squared plus 30, and we're going to have x times f of x. Just hit the x on that. Don't control enter because you need an exact value, and your exact value is right there. Now for a nasty one with part J. So there is a transformation that has been applied here, which is often the cause of many students' worries. So we have the serving speed of a grade B ball given by this transformed state. We're told the mean of the grade B ball is going to be 2 pi squared plus 8 in meters per second, and we have to figure out what would A be and what would B become. So how do we achieve that? Well, one thing worth mentioning off the bat is the fact that this W here is not any different really speaking, to this V. It's just the variable that is of the function. So whether it says W, whether it says V, we can kind of ignore that because it's like saying f of x. It's just one of the variables that are involved in there. The ones that we care about are the A and the B. Now, one thing we're told is the mean of this equation. So one thing we can do, we can get one equation by simply saying that from our upper to lower bound, so I'm just going to put in some, in fact, yeah, let's start writing this out so it can be a bit easier to see what's going on. So integral from lower to upper of x times our new function, which is f of x over b, a times f of x over b, sorry. We put the a at the front, I suppose. That doesn't really have to be in the integral. It is just a constant, after all. A times x times f of x over b dot dx, and that is going to equal 2 pi squared plus 8. 2 pi squared plus 8. Now you notice that I didn't specify what the upper and lower bound were, and that's going to bring me to the next section here, which is, what is this all about? This x over b. Why have I elected not to do upper and lower bound? It's because that division by b impacts your domain. So instead of being from 30 to 3 pi squared plus 30, 3 pi squared plus 30, we now have x over b in the center of both of those. And so, if you want to figure out your new upper and lower bound, well, that's going to come by multiplying everything in there by b to get the x on its own. 30b less than or equal to x less than or equal to 3 pi squared plus 30b. That's going to give us our new upper and lower bound. So upper is going to be that one, lower is going to be that one. But okay, that's one equation. What else can we do? Well, we still know that the total probability under the graph needs to equal 1. So this one here was a mean equation. X times f of x with the new transformed has to equal that with the new upper and lower bound. We also know that the total area under the graph has to equal 1. So again, a times the integral of our upper and our lower, just f of x over b this time, no x times, and that has to equal 1. So that's equation 2, that's equation 1, 2 unknowns, 2 equations. What we're going to have to do from there is simultaneously solve. So menu 3, 7, 1, 2 equations. We want a, whoops, let's get that on screen properly. Let's get it there-ish. There we go. A and b. And now for our integrals. So it is a times the upper, which was bracket 3 pi squared plus 30 times b. 30b was our lower one. And the function was x times f of x, but it was f of x over b because of the transformation. And that specifically was being equated to, where is it? 2 pi squared plus 8. 2 pi squared plus 8. And then we just do a very similar thing down here with that second integral, this one. A times shift plus, let's grab a copy of this because that'll be maybe slightly faster. Control C, Control V, 30B, and then we're just having f of x over b dot dx, and that has to equal 1. Now we need find the values of a and b, which means they'll be exact values. So all we've got to do is hit enter, and that's going to give us our two values. A equals 3 over 2, and b equals 2 over 3. 5a is going to be pretty quick. So we have some function f of x, and it's being transformed into g of x. So you want half times f of 2 take x instead. That's your transformation. And we have to create the, or at least a possible sequence of transformations to get from f to g. We're already told that the dilation factor of a half has to happen first. So that kind of locks us into at least how we started out. We have to have that dilation at the beginning. So sometimes you can do TRD, sometimes you can do DRT, depending on if you do translation reflection dilation, or the other way around. There are ways to do both. In this case, we have to, well, we should approach it in a DRT fashion because we're starting with dilation. Well, okay, so if we're doing DRT, there's only one thing that we need to make sure that we do, and that is to make sure that everything is fully expanded. So if this is our x comma y, then we need to make sure that whatever's going on here, ax plus b, cx plus d, whatever that is, has to be expanded like that. You don't want to have any factorizations like this going on. C bracket x plus d on c. Right, that's bad if you're doing DRT. DRT needs expansion out. But okay, we do have that. We do have that expanded thing allowing us to use DRT. So what are we going to do from there? Well, we have a look at our reflections. Do we have any? Yes, we have a reflection on the x value, which means we specify that as a reflection. Look, the CT reflection in the y axis. The reason why is because if you have a little axis here, you have a dot, the y-axis acts like a mirror, causing the y values to remain the same, but the x values change. That's why the x is what gets the negative in that case. So reflection in the y-axis. And then lastly, this one can be a bit tricky because when you see that positive 2 there, you might be expecting that is a shift left because it's positive. This is kind of why I usually don't like doing things by recognition like that. Because when you do DRT, you have to expand out. But if you want to figure out what's going on in the function notation, you have to factorize, which means you have to rewrite it as a half f of, well, not x, but negative bracket x take 2. Like that. You have to take any coefficients off of the x to see what the true translation term is, which in this case is a shift right by 2. Right by 2. If you want to be very specific with the terminology here, you would have to say a shift. You would have to say a translation 2 units to the right, or you could say a translation of 2 units in the positive x direction. That obviously takes a fair bit of time to write out, so if you're short on time, my recommendation is just to write this, put a little star on the question, and then come back to it later. Bit of an interesting one here in part B. So we have two functions, g1 and g2, which have the exact same rule as g, but they have different domains. g1 is going to be the strictly increasing portion of our function g of x, and g2 is going to be the strictly decreasing portion. Specifically, we care about g1, specifically even more, the domain and range of the inverse of g1. Well, okay, one thing we can do to figure that out is to start with saying what actually is g of x. We've only kind of just played around with the transformations that were applied to it, so let's actually figure out what g of x would be. To do that, we're going to start by defining f of x. So f of x was e to the x plus e to the minus x plus, there we go, it's a bit better, e to the minus x. And then g of x was the transform state of that. So g of x was a half of f of 2 take x. Yeah, that's what that was. So if we then reprint g of x, we see we get some nastiness there. The reason why finding g of x first matters is because if you want to find domain and range of an inverse function, you first want to figure out domain and range of the original and then just flip those around. Now, more specifically, we care about where this one is going to be strictly increasing. So let's first figure out where is this strictly increasing. If we plot g of x, we're going to get some sort of parabolic shape. So all we have to do is figure out where is this turning point, and then that will allow us to say, well, okay, everything to the right of that turning point is going to be the domain of g1. You can do that a bunch of ways. You can use the analyze graph tools to find a minimum. The reason why we typically shy away from that is because it won't give you, it'll be very hard to figure out if you have an exact value or not, because it'll only really show integers as exact values. Now we did get lucky with this one. It was a perfect exact value there of x equals 2. But more nicely, you'd want to come over here and use the calculus tools. So you want to do your f min in this case. So option 7, you put your g of x, comma, x, and then you can be even more certain that it's x equals 2, and not 2.0000 something or other. But okay. We know everything to the right of 2 is going to be the domain of g1. Oh, yeah, domain of g1. So let's write that out just so we don't forget it. Dom g1 is inclusive of 2 to infinity. Cool. Next up, we need range of g1. Range of g1. Well, if we look back to our graph, that shoots off to infinity, and this has a y value of 1. Now, we can double check to make sure it's a y value of 1 and not 1.00 something or other. If you want, you can then just go g of 2, and sure enough, you get 1. So all that means is that our range is from 1 to infinity. So if you want to find the domain and range of the inverse, you just swap these around. So you would say domain of g, what do you call this? g1 inverse is 1 to infinity, and then the range of g1 inverse is 2 to infinity. Now we get into the fun part, CI, finding the coordinates of P and Q. So what's going on here? Well, we have g of x plotted on our graph. We also have the inverses g1 and g2 also plotted on that graph. The reason why there had to be two individual inverses there was because, well, the inverse can only ever be a one-to-one function. And so if you were to find the inverse of what appears to be a parabola, you would then get a parabola in the pointing in the x direction as opposed to the regular parabola that would point in the y, and that would not be a one-to-one function. But anyway, P and Q, those are just the intersection points between our inverses. And so what we have to do is figure out how to find those intersections. Well, one nice and easy way that we could think of would be to simply equate the inverses to the original, and then that would give you P and Q respectively, where g1 equated to g of x would give you the inverse of g1, I should say, equated to g of x would give you the q, and then the inverse of g2 equated to g of x would give you p. Better than that, whenever you find intersection points between a function and its inverse, all you ever have to do is equate it to the line y equals x, because it will only ever intersect along the line y equals x. That's what this bit here is telling you. It's identifying, or at least it's prompting you to understand that this will only ever intersect along the line y equals x, and so we can save some time by just equating to y equals x. So we have our g of x. All we're going to do is equate it to x and then get our 2 points. So menu 3, 1, g of x is equal to x, comma, x. Control enter so we can get our proper solution. And it's going to give us x equals 1.27 and x equals 4.09. Remember, we are doing correct to 2 decimal places. Now, the key thing here is we needed to give the coordinate, not just the x coordinate. Well, if it's along the line y equals x, it means that the x value is identical to the y value. So the coordinate for the first is going to be 1.27, comma 1.27. And the coordinate for the second is going to be 4.09, comma 4.09. We can actually use a very similar thing for part CII. We're trying to find the area of the region bound by G, the inverse of G1, and the inverse of G2. So pretty much we're looking for all of this bit in here. Right, here's our inverse of G1, that gives you this upper bound sort of thing. You've got the inverse of G2, which gives you this lower bound bit, specifically just that bit. And you've got g of x, which gives you the bold bottom bit underneath. We want to find all the area contained within that perimeter. Well, again, that would be kind of complicated if you were just to try and do that using the regular method, which is your top take bottom of the entire shape. You know, you can't really just say, okay, g1 is top for the whole thing. It doesn't really quite work that way. There's a lot of different curves that come into play. We can further leverage the line of y equals x to help us out here. Because if we just look at the component y equals x and g of x, that little section of area is purely bound by those two curves. There is no crossover of curves, there's nothing else we have to worry about. So all we're going to do is say our top is y equals x and our bottom is g of x. That's going to give us that first half. Now, you can double that to then find the second half as well, inclusive of the full area. The reason why is because, again, these are symmetrical about the line y equals x. That's how inverses work. And so by finding this first half, you can therefore find that second half by simply just, well, you can include that second half by simply doubling your result from the first half. So let's just do that. So we're going to do Shift+. We need our lower bound and we need our upper bound. Well, how do we achieve that? We found those earlier here. So we're just going to do our best to copy and paste those values in. Now, you don't have to copy the whole thing. That would be a bit extreme. It's not necessary to do the whole thing, but I kind of like to do it anyway, just to make sure I'm definitely not going to get any rounding errors. The reason why the lower and upper bound work is because, well, if you look at that little half there, it starts at P and it ends at Q. So we're going to use the coordinates, or the x coordinates of P and Q. Then it's just x minus g of x. Dot dx, Control Enter, 2.78, which, now that we have the 2.78, all we're going to do from there is double that, because, well, we only found a single half. We want to find the whole thing. So from there, our new result is going to be 5.56. Okay, bit of an interesting one in part D. We're told that the turning point of some new transformed version of f of x is going to always lie on the graph of 2x to the power of n, where n is an integer. So how do we figure that out? Well, we are told specifically the turning point of h will lie on that graph. So one of the first things we should probably do there is figure out where that turning point is, which is going to be a matter of just subbing in, or just finding the derivative of h and then setting it equal to 0. So let's find h. h of x is equal to 1 over k f of k take x. K take x. If we then try and find where the derivative is equal to 0, solve for x, that's going to give us something to work with. F of x equals 0, comma x. Oops, I did the wrong one there. That should be h of x, not f of x. h of x. It's going to give us x equals k, where k does not equal 0, which is fine for us because we know it can't be 0. It's non-inclusive of 0 at that spot, or at least in its domain. So how does that help us? Well, it does allow us to sub that into our function that we've just obtained. So let's just do that. We have our new h of x, and specifically, we know our turning point occurs at x equals k. So the corresponding y value of our turning point will be 2 over k. Now that we have that y value, all we're going to do is sub that into our function, y equals 2x to the power of n, because we now know what our y is equal to, and we now know what our x is equal to. That gives us one thing left to solve for, which is just n. So let's give that a shot. Menu31, y, which is 2 over k, equals 2 times x, which is now k, to the power of n, comma n. Now if you just hit enter, doesn't matter what you do there, it's going to give you something a bit nasty there. It's not quite the value of n, even though it is a value, technically speaking. What you want to do is tell your CAS that k is greater than 0. Even though it knows k is greater than 0. If you don't tell it, it won't give you the answer we're looking for. So we say given k greater than 0, hit enter one more time, and that's going to finally give you the solution that we needed, which is n equals -1. And finally, we have E, which is quite possibly the hardest question in this entire exam, which is nice of them to only give it 1 mark. So what are we doing here? Well, the rule of our inverse is given by that nasty function. And we want to figure out, more or less, what's it going to take for this graph to intersect the inverse of the h1. Right? What kind of k value will it take to do that? Specifically, what's the smallest k value? Well, what does that actually look like? Ideally, we should graph this. So I'm just going to call this O of x, just because what else are we going to call it? Going to call it natural log of k over 2 times x plus a half times square root of k squared x squared, so k squared x squared minus 4, and then out of all of that is going to be a plus k at the very end. Now, just to help us out a little bit, what we're going to do is do a bit of graphing. We're going to plot our h of x, we're going to plot our h1 of x, and we're going to just see what's going on. Or at least the inverse of h1, I should say. So, first up, h of x, we're trying to plot h1. And h1 specifically goes from k to infinity. So, I'm going to give that as our domain. So, x is going to be greater than or equal to k in this case. X is greater than or equal to k, given, x greater than or equal to k. You have to create a slider for it, which makes sense. And then we can plot, h1 has no such issues. So we're just going to do O of x as normal. Cool. Okay, so we have our two graphs, and we can see off the bat they don't touch. Right, there is no touching there involved. So let's see what happens as k changes. What's it going to take to make them touch? If we get bigger, they appear to, well, that worked. K equals 2 is going to get them to touch. And then you can imagine as k continues to get larger, they'll still touch at one specific spot, but only but further apart. If we go k equals 0, it can't be, and k cannot be negative, so we don't have to worry about that. So if we're just messing around with this, we see that k equals 2 is a pretty decent candidate. Now if we play even more, we saw k equals 1 didn't quite work. What about k equals 1.1? Just so we can get an idea of what might be going on. It gets closer, but not quite. 1.5, it finally flips. So we see at some point, it causes the graphs to flip on each other. That's basically what's going on. Now you could play this over and over again until you eventually get the correct number, but that will take way too long. You won't have enough time to do that. So, all these kinds of questions where the inverse has to intersect the original, there are two criteria that you need to meet. One is that the gradient needs to be, basically overall it needs to be tangent. They need to be tangent to each other. And the only way they can be tangent to each other is if they are tangent to the line y equals x, which means two things for us. Firstly, it means our gradient at that point needs to be equal to 1, since it's tangent to the line y equals x. And secondly, it means that the graphs have to intersect. So let's go forward with that understanding. If we go back and make sure to delete the variable of k so that doesn't cause any issues, we're going to look at that gradient thing first. So, menu 31, we want the derivative of, it shouldn't matter what function you choose. Sometimes the cas can play up depending on which one you choose to do. It doesn't really matter at the end of the day. Both functions should be intersecting the line y equals x, so it shouldn't matter which one you do. But okay, derivative of the inverse in this case is equal to 1, comma, x. Okay, that's good. So it's given us some nastiness there, so maybe we should make sure that k is greater than 0. So let's just tell it that. K is greater than 0. Okay, that hasn't really changed much, but that's okay. We can still clearly see that it's plus or minus the square root of k squared plus 4 all over k. Those are the things that are valid for us. Now, we know that k has to be greater than 0. And so, sorry, we know the x, that's what I should have mentioned. We know that whenever we were playing with it, the x value was always positive. Right, so if we play it over here, well, it's not going to show it, but we saw intersection points over here. There wasn't anything that would cause it to go negative. And so that's the reason why we have to pick the positive root rather than the negative root. Well, what do we do with that? This has given us x purely in terms of k. So now what we have is, if you look at what O of x actually looks like, it's got two variables in it. It's got k and it's got x. When you sub in this x value in terms of k, you now only have one variable, which makes it actually solvable. So we figured out what it takes to be tangent. Now we've got to figure out what that coordinate would actually look like. Now we've got to figure out where that intersection point would be, and we can put that in a solve. So let's do exactly that. Use the same function because why not? I'm going to say O of x is equal to x, comma, now we're going to say comma k, and what I'm going to do is instead of going through and putting the k squared stuff into the x's, I'm going to put that as a conditional at the end. You can just sub it in, it's fine, it doesn't do anything spectacularly differently. I'm just adding it at the end because, well, just because I've done it before that way. So given that x is equal to that. We hit enter, it's going to complain, hit control enter, see if that does anything better. You'll get a bit of a spinning wheel, but if any luck, we're going to get our k value that we care about. In this case, we get two different k values, one of them being negative, the other, of course, being positive. Only one of those is correct. If you look back at your domain for k, which is from 0 to infinity, you can only have that positive answer. So for 2 decimal places, that's going to give us 1.27 for our k value. Now, for the actual finale, which is part F. So we're told that at k equals 5, the two graphs will intersect twice, and we need to find the area of the region that is bound by those two curves when k equals 5. And, well, we're giving it to 2 decimal places, but whatever. So one of the first things we can do off rip is just set k equal to 5. Nice and easy. If we go back to our graph, we should identify that in fact they do intersect twice. Our domain isn't quite right for that, so what we're going to do is, let's keep that as -10, shoot this off to 100, and then shoot this up to, I don't know, let's say 25. Okay, that was a bit ambitious. So let's just zoom in a little bit better. Let's say 20. Cool. Okay. Now that is interesting because we're told that there are two intersections for k equals 5 and we haven't got that. So what's going on here? Ah, I've seen it. So they said the graphs of h and the inverse of h1. What I've currently got here is the graph of h1 and the graph of the inverse h1. So to make things a bit better, what I should do instead is get back into this and remove this conditional here. Oh, hopefully it doesn't break anything if I hit enter. There we go, that's better. So just a quick reiterate on what that was. It said the graph of h, where h was this thing. That was defined for all real numbers, whereas h1 was defined for just k up to infinity. But okay, we're finding the area bound by this curve, which is nice and easy. We could theoretically use the graphing tools for this. We could just go menu 6, bounded area, click on this point once it stops freezing. Oh. Click on that point and click on this point, and that'll give you the answer that you're looking for, which you can use as your final answer, of course. Oh, whoops. Oh no, I've clicked it too early. Terrible mistake. Is this going to work? That might not be totally accurate, but point being, you could click those points and get an answer. But the reason why we can't just do that off rip is because this is a 2 marker, and so if all you put on the paper was 43.91, well, you might be in a bit of trouble. You get 1 mark at least, but not a mark for answer. And so one of the things you can instead do is set the integral. So this is just a classic case of top take bottom. You can see that O of x is clearly on top, or in this case, our O of x is their inverse of h1, and you can see that h of x is bottom. And so all you would do is say the integral from upper to lower, we'll look at that eventually, of, let's say, so that the inverse was on top, so you'd say h1 inverse of x minus h of x dot dx is equal, yeah, you could say like the area A is equal to that. As for what do we do for the integrals, let's initially put them as x1 x2, just so we can show some working for the actual test. All you would do from here is say x1 equals whatever it ends up equaling. So you just want to do the intersection points, which means you'd say x1 comma x2, do a little colon, and then you would just say h1 to the power of negative 1 x, or h1 inverse of x, equals h of x, x1 equals this, x2 equals whatever that equals. So let's go ahead and do that. So we're doing menu 3, 1, O of x is equal to h of x, comma x, control enter, because it's going to break otherwise. We're going to have our 1.45 and our 8.78. So you do your 1.45, 8.78, and then finally you would plug those in as your integral. It would say area A is equal to 8.78, 1.45, h1 inverse minus h of x, and then just give whatever that actually becomes. Shift plus. Now when you actually do it, you want to grab the entire value. Don't round early. That's just for putting it on paper. Control V. Whoops, clicking the wrong buttons there. Control C. H inverse was O, and the original H was that. Dot dx. Control enter. That's going to give you an answer of 43.91, which, if you compare back to what this was, remember I clicked it a bit early, so it's going to be a bit off. Actually, that is 43.91, isn't it? 43.91, 43.91. Nice. So I did manage to fix it up.